Today on How It's Made. Solid tyres. A factory where they set the wheels in motion. Cheesecake. This is no half-baked idea. Canoe paddles. See if these float your boat. And globes. At this factory, they're always on top of the world. But first, the solid rubber tyre is designed for off-road conditions, like construction sites, landfills and warehouses. These areas are full of hazards that would flatten ordinary pneumatic tyres. But solid tyres can't get a puncture. They just keep on turning. And that's good for any job site. No air in these tyres means they're ideal for heavy work. They can move a lot of weight around without buckling. Construction begins with a wide, flat strip of partially processed rubber. A hot extruder forces it through a series of holes. This transforms the rubber strip into a narrower, rounder form. The rubber falls between hot cylinders, where it's rolled out, thin and soft like pastry. In another part of the factory, the tyre's metal framework is prepared. They're moved along on an overhead rail into a special chamber. Steel pellets are shoveled in. Inside the chamber, a machine tosses the pellets about and the friction polishes the metal tyre frames. A coat of primer is sprayed on, and an adhesive is applied. Next, one is mounted on a mechanical arm that's positioned in front of the rubber rolling system. The arm moves the tyre frame forward to meet the turning cylinders. The surface, still tacky from the glue, takes up the freshly rolled rubber. It layers the rubber around the tyre base up to 100 times, depending on the tyre being made. Then it's weighed, and pieces of rubber are sliced off until it meets the right specifications. The solid tyre is now in good shape, so it moves on to the next stage. Over at another station, a different type of solid tyre is being built. This one has no metal framework, so it will fit on a wheel rim made for a pneumatic tyre. Rubber strips are wound around a metal hub that serves as a mould. A bar presses down on the rubber wrap to eliminate air pockets. These rubber strips contain recycled material, which is stiffer. This will help the tyre hold its shape. For these tyres, it's time to get a grip. The process of adding tread to the tyres begins as a release agent is sprayed onto a mould, making it easier to remove the tyre later. The ID label and serial number plate are lightly glued in position for transfer to the tyre. The tyre is then centred in the mould with a metal ring. Then the top section of the mould is lowered onto it. And the mould is hoisted to another station where it's sandwiched between two hot plates. The combination of heat and pressure melts the rubber into the crevices of the mould. The rubber cures in minutes. The process has also vulcanized the rubber, a molecular change that strengthens it. It takes a specialist to change one of these tyres. Using a hydraulic system, he removes the old tyre from the wheel rim and installs a new one. A solid tyre on a wheel rim made for an air-filled one. Large tyres with metal framework go into this autoclave to take shape and undergo vulcanization. A forklift truck, equipped with solid tyres of course, extracts the finished tyres from the autoclave. And now, they're ready to roll. The ancient Greeks served cheesecake to the athletes of the first Olympic Games in 776 BC. The Roman conquest spread the dessert across Europe. These tasty treats have stood the test of time. From New York delis to fancy dinner parties, the cheesecake suits all tastes. The ancient Romans were so enamored with cheesecake that they even brought it to their temples as an offering to the gods. The cheese in cheesecake can be cottage, ricotta, Neufchâtel, or cream cheese. Their base, a buttery biscuit crust, is similar to shortbread. For a batch of about 60 cakes, this bakery combines 23 kilograms of butter with 4.5 kilos of sugar. Next, 16 egg whites. Then 11 kilograms of flour. After mixing just long enough to incorporate the flour smoothly, the dough is transferred via conveyor belt to a vat. Gravity pushes the blob of dough out through a slot at the bottom, expelling a dough sheet about 0.5 centimeter thick. A dusting of flour prevents the dough from sticking, not just to the conveyor belt, but also to the rolling and cutting tools. This prickly roller perforates the dough sheet. The holes enable trapped air to escape during baking, which prevents the dough from shrinking and ensures a flat, bubble-free crust. The next roller has plastic circles which slice the dough into cake-sized discs. The leftover pieces go into a new batch of dough. Each dough circle goes into a pan, then bakes at 190 degrees Celsius for 16 minutes. Meanwhile, the batter takes shape. For a batch of about 20 cakes, the bakery combines 11 kilograms of cream cheese with a kilo of cultured sour cream. That's sour cream processed a little longer than usual to give it more flavor. After slowly mixing in 7 kilograms of sugar and around 2.5 cups of flour, 3/4 of a cup of vanilla extract is blended in. Then it's time to get cracking with 18 whole eggs. That's the recipe for plain cheesecake. Flavored versions contain extra ingredients. This batter is caramel pecan. It goes with a chocolate crust. As the baked crusts arrive, sprayers grease the inside of each pan with butter so that the cake will slide out easily after baking. Then a machine called a depositor shoots in just the right amount of batter. The pans now enter a tunnel-shaped oven that's 21 meters long. The temperature inside is 177 degrees Celsius. By the time the cakes exit the other end, they're fully baked. These 25 centimeter wide cakes take just under an hour. From the oven, the cheesecakes go onto a cooling conveyor. By the time the hot cakes, up to 2,000 at a time, have completed the nearly hour-long circuit, they're at room temperature and ready to come out of their pans. From there, it's straight into the storage freezer, except for certain fancy cheesecakes, which detour to the decoration department. This Belgian chocolate cheesecake gets a big squirt of chocolate ganache, a decadent mixture of chocolate and cream. It's spread all over before swirls are made with a decorating comb. And now the final touch, a sprinkling of cocoa. Certain orders go into an automated cutting machine that divides each cake into 14 equal slices and inserts grease-proof paper in between them. Back at the decorating department, they're putting shards of chocolate on a mud pie, a combination chocolate souffle chocolate cheesecake with pecans and a coffee mousse topping. You might want to put off that diet for just one more day. Coming up on How It's Made. Canoe paddles. Don't get stuck up a creek without one of these. And globes. We nip down to a factory that should be world famous. See you after the break. Welcome back to How It's Made. The simple paddle is made with sophisticated craftsmanship. Today's wooden paddles really go the nautical mile. They keep us from going adrift, and no one wants to be up the creek without one. Let's face it, your canoe is going nowhere without it. With paddles like these, you really can go far. These days, paddles are often a blend of hard and soft woods, giving a result that's strong yet lightweight. The boards are fed into a multi-bladed ripsaw that slices them into a uniform strip. Each strip has a flat, smooth joint on the side. Glue is rolled onto these flat joints and then strips are pressed together. These glued sections will be used to make paddle blades. Over at another station, they're working on the paddle shafts, 2 at a time. Shorter pieces of wood, which will become the handles, are glued and clamped together. The blade chunks are arranged in a much larger clamp. Then the glue-coated ends of some shafts are wedged between the blade pieces. In a process called lamination, the blades are bonded to the shafts. The laminated paddle shapes are called blanks. The blade design is penciled onto one of the blanks. The design is cut out using a bandsaw. Laminated wood doesn't warp easily, which means the paddle blade can be made wider to give more power to the user. The more traditional look and feel of paddles cut from single pieces of wood are still favoured by some. This narrower paddle has been cut from a piece of cherry. Modern tools make quick work of a design that's hardly changed over the centuries. In no time, the basic paddle has been carved from a single piece of wood. A large router is used to round it off. It shapes and contours the paddle to its final dimensions and gives it a smooth finish. In just minutes, that chunky-looking paddle is transformed. Meanwhile, back in the laminated paddle department, a saw cuts slots in the tips of each one. A liquid plastic concoction is mixed up. Then it's poured into the slots where it hardens. The plastic gives the paddle tip some extra protection. Now it's time to improve the profile of the laminated paddles. With the same type of router used to shape the solid paddles, the design is fine-tuned. Both types of paddle then get a heavy sanding. Each one is tapered so that it's much thinner at the tip. The trademark information is branded onto each paddle using a hot iron. Then it's time for the paddles to take a dip in a tank of varnish that contains a sunblock. The varnish both protects the wood and enhances its natural beauty. The paddles are suspended on an overhead conveyor. And soon they'll be on their way to a waterway near you, where they'll be sure to leave ripples of approval in their wake. Because the world is round, flat maps don't give us the full picture. A globe gives a more accurate impression of the world. It depicts countries in true spatial relation to one another, and better defines lines of latitude and longitude. Globes really give us a well-rounded view of our planet. At the Globe Factory, production revolves around world events. As wars and political upheaval redraw boundaries, these spherical maps are revised accordingly. Making a globe begins with a large roll of cardboard. A machine pulls it under a roller that coats it with glue. A knife then slices the cardboard into smaller pieces, which will serve as liners for the maps. One more coat of glue, and then the liners are stuck to the back of maps. Heated rollers press them together, completing the seal. Each map is of a hemisphere. A powerful press now cuts the maps along pre-marked lines. Each map is carefully positioned in the cutting press. After all, one false move and they could lose parts of Japan. It takes 2 punch cuts to do the job. The excess paper is pulled away from between the 12 spoke-like sections of the map. Here's a top view of that cutting press. It acts like a giant fist to punch out the maps. And now, it's time to shape the world. A map cutout and a separate liner are placed in a mould of half a globe. It rises into a heated cavity where it's pressed into a bowl-like shape. Now they have a hemisphere. But of course, there are two in every world. At least mine. The southern hemisphere is made using the same type of mould. The moulds also emboss each map to signify peaks and valleys on the Earth's surface. Here's an inside look at those moulds. The raised and indented sections make impressions on the globes. They allow people to see and feel variations in the world's topography, both above ground and underwater. The hemispheres are complete, and it's time to go global. A northern hemisphere spins while a razor blade trims the edges. Then a lower hemisphere goes for a spin, while a nozzle beads hot glue along the inside. This stiff cardboard ring adheres to it and gives the hemisphere some reinforcement along the equator. Glue is applied to the northern hemisphere, and it fits over the ridged edge of the southern one. The two halves are precisely aligned and tape is added over the seam. This disguises it and marks the equator. Next, each globe is mounted on a pedestal that's attached to a metal arc called a meridian. Suction to the top of the globe, the meridian will allow it to revolve. From fragments of paper and cardboard to a globe. This world was made in just a couple of hours. Globes tell us where we are in the world and help us figure out where we're going. Globes are produced in many different languages because there is, well, a worldwide demand for them. And because they help us get our bearings, you could say they make the world a better place. So, whether it's a tiring process you're interested in, or perhaps a recipe courtesy of ancient Greece, or you just fancy going for a paddle, now you know how it's made. Today on How It's Made. Boomerangs, designed for a good rate of return. Barbecues, all the juicy details about how they make them. Pinball machines, we go to the factory to check out the game plan. And strobe lights, a very flashy product indeed. But first, boomerangs have come a long way over the years and are now finely crafted gizmos. Originally, people threw sticks to hunt, and that's probably how they discovered that certain bent sticks would circle back. You could say that the boomerang is a bit of a throwback to primitive times. Boomerangs come in many shapes and sizes. Production begins with a solid piece of wood. Here, the growth rings are highlighted to demonstrate that the later growth is narrower. This means it's denser, so it will be easier to work with. The woodworker takes 16 strips of that dense wood and places them in a steam box for 20 minutes. The steam makes the strips much more flexible. They're so elastic, they can be bent by hand. Watch how he arcs all 16 layers at once, with very little effort. Now he has the basic form of a boomerang. To improve the contour, he clamps the strips in a boomerang-shaped mould. They remain clamped for a day or two, long enough to dry and harden into the bent form. He spreads glue onto each bent strip, then clamps them together in the mould again. This time the mould has been coated with wax to prevent the glued strips from sticking to it. It's left to set overnight. Then the laminated boomerang shape is removed. It's solid, but far too chunky to fly. The woodworker slices it into pieces 10 millimeters thick. The piece of laminated wood yields about 6 thinner pieces. Each one is light enough to be a boomerang, but it needs more form, and he has to get rid of those rough edges. So he outlines a more refined design and cuts it out. But there's an easier way to make a boomerang, with sturdy aircraft plywood. With plywood, there's no need to laminate and then physically bend the wood. He simply cuts out the pattern, then sculpts the tops of the wings with a drum sander. He's made the tops of the 2 wings curve upwards, but in opposite directions. It's this contouring that will make the boomerang fly in a circle. On some models, embedded lead weights help to balance it. The laminated boomerang gets the same contouring, but a file is used instead of a drum sander. Laminated wood responds better to this technique, but it's much more labor-intensive and it takes skill. One mistake in the shape and size, and it will throw off the aerodynamics of the boomerang. But our woodworker has the job down to a fine art. To tune the boomerang, he softens it over a steaming kettle while twisting the wings into an upward flip, similar to an aeroplane wing. This blower dries the wood to ensure it stays flipped. He then sets the boomerang on a flat surface to check the curve. He sprays sealant onto the boomerang and finally, he gives it several coats of lacquer for a high gloss finish. And now these boomerangs are ready to run rings around the competition. The origins of the barbecue are clouded in a bit of a smoky haze, but it's believed the Caribbeans were the first barbecuers. Of course, back then they didn't have charcoal grills. They roasted their meat over a smoky pit. Today there's nothing like a barbie in the garden, and the taste of incinerated burgers. Production of a basic grill begins with large steel discs. A machine with rollers coats each one with a soapy lubricant. Then they're fed to a press that stretches the disc into a bowl. Stretching steel is a bit tricky. It could tear if they don't lubricate it well enough. So each disc gets a generous application before it goes under the press. The press swiftly transforms the flat piece of steel into a round bowl. This is a back view of the press. Using mechanical might, the ram delivers 500 tons of pressure. A similar type of press is used to make the lids for the barbecues. An operator inspects each part for splits and cracks. Then it's over to a press that trims the rim. The scrap pieces are tossed into a bin for recycling. Next, the barbecue bowl is spun while an automated roller flanges the rim. After that, the bowl is perforated to make holes for ventilation. Now they bring out the welding guns. The guns fuse metal couplings to the bowls to serve as attachments for the barbecue's legs. Here, handles are loaded into a fixture. A turntable swings into action and delivers the bowl to welders that fasten the handles to each side. At another station, they're working on the barbecue lids. A handle is welded onto each one. This one will allow the chef to lower the lid to control the cooking temperature, and then lift it again when it's time to flip those burgers. The barbecue parts now travel on an overhead rail to the wash station. Here, nozzles hose them down with soapy water and then rinse them. Once they're dry, they head over to the finishing department, where they are dusted with a glass powder. Then it's into a furnace that's 848 degrees Celsius. The furnace bakes the glass dust into an enamel finish that will protect the parts from rust and stains so they'll last for years. Next, they go under lights which expose any defects in what should be a mirror-like finish. The technician examines each part, inside out. A punch machine now makes dampers from aluminium. It simultaneously cuts the shapes and embosses the company's trademark onto them. A damper is a handy attachment that enables the chef to control the flow of air to the grill. Nylon grips are put on the handles, and the damper is installed over the lid's ventilation holes. It's up to the consumer to do the final assembly, something that should take just a few minutes before all your mates arrive. Coming up on How It's Made, we ask, why are these people so busy? And why is this woman breathing fire? See you after the break. Welcome back to How It's Made. Before video games, the pinball machine reigned supreme. The action is real and not on a screen. You pull a plunger and get the ball rolling. You hit flippers and navigate bumpers, all to the clamour of clanging bells and flashing lights. No wonder it's not yet game over for pinball. The game of pinball is unprogrammed and unpredictable. Reams of wire make up the pinball machine's electronics. There's more than 3/4 of a kilometre in one model. Different types of colour-coded wire are used. They're wound around pins and attached to the connectors on the circuit board. There's a detailed set of instructions and an engineering drawing to keep things from getting in a tangle. The wires are removed in loosely tied bunches. This allows them to move freely as the tips are soldered together. Not all wires are soldered. Others get attachments called lugs. These are crimped onto the ends of the wires with a hydraulic machine. These lugs will be used to connect wires to attachments on the playfield. The cable is hooked up to a testing board and every circuit is checked. The playfield, adorned with colourful art, is placed onto a bed of nails with foam strips. The nail bed rises and presses against the header. The nails prick the back of the board, but the foam strips stop them from going through. These nail holes will serve as markers for installing pinball targets and tactical features on the playfield. Next, a few holes are drilled, and the playfield is covered with a metal template to drill more holes. These will be used to mount some of the pinball gadgetry onto the playfield. Anchors are hammered in to attach the metal railings that keep the silver balls from rolling off the playfield. There's a lamppost, followed by some plastic bumpers. 115 flashing lights are installed. Now it's time to permanently attach all that wiring. Some are soldered directly onto the board, others are fused to switches. A speaker is bolted into the cabinet for some major sound effects. The spring-powered plunger goes in next. Without it, you couldn't take your opening shot. A toy villain is attached, and a ramp in the shape of a sword is added, along with a few other toy characters. The ball is run into every target and mechanism to test the switches. There can be up to 70 switches in a game. Every button is pressed as a computerized system diagnoses any malfunctions. Nothing is overlooked. If everything works, the playfield is then slid into the cabinet. It gets a shatterproof window because it could take some abuse from enthusiastic gamers. A metal bar is used to lock it all down. Finally, the header is mounted and this pinball machine is wired and ready for action. Mention strobe lights and a 70s disco comes to mind. But you also find them on aircraft wings, on police cars, and on towers and tall buildings to warn low-flying aircraft. They even play a role in photography and on factory production lines. Most enlightening. A strobe lamp emits repeated flashes of high-intensity light. At this factory, production begins with glass blowers. Using a ribbon burner, glass tubes are heated to 1600 degrees Celsius. This softens the glass for bending into a specific shape. At the same time, air is blown through a rubber hose attached to one end of the tube. A cork in the other end traps the air inside. This builds counter pressure to prevent the tube walls from collapsing inward as the glass softens. The size and shape of the glass tube varies by model, but its job is always the same: to house electrodes, wires, and xenon gas. The electrodes conduct the current, which charges the gas with electricity, making it illuminate. This factory makes several models, some in large quantities for the mass market, others in small quantities, custom designed for specific clients. With mass-produced models, after glass blowing, automated machines take over. Custom orders are handmade from start to finish. Even the electrodes are made manually. A precise amount of metal powder is weighed out and poured into the cavity of a press similar to those used by pharmaceutical factories to make pills. This powder is a blend of several different materials, but the company won't divulge what they are. The press applies 4 tons of pressure, compressing the powder into a pellet. The factory inspects every pellet to ensure it meets quality standards. The pellets then undergo a process called sintering. They bake for 9 minutes in a hydrogen-fueled oven. Hydrogen because it burns at high temperatures. The 1700 degrees Celsius heat fuses the powder particles into a solid unit that won't crumble apart. Next, a wire is welded to each electrode. 2 electrodes are inserted, one for the positive current, one for the negative, into each glass tube. Then the end of that tube is melted closed. Then a wire called a trigger lead is attached. It works like a car's ignition, prompting a transformer to send a high voltage electric pulse to the electrodes, illuminating the gas. This automated machine assembles the factory's mass-produced models. Before it's set in motion, the components are loaded. A pair of electrodes made by an automated pill press, and the glass tube on top. Now the machine takes over. It vacuums out the air in the tube, then injects xenon gas, then melts the glass tube closed under the electrodes, then cuts off the excess glass. The tube's interior must be completely free of contaminants for the gas to illuminate, so just before the vacuum fill and seal operation, a hot coil encircles each tube to burn away any impurities. On custom-made models, all these steps are carried out manually. The strobe lamp is finished and ready for installation. This model is for those warning lights you see on tow trucks and road construction vehicles. It goes into a glass reflector lined with metallic film. A transformer regulates the voltage. Its 3 wires connect to the positive, negative, and trigger leads, protruding from the lamp. A glass lens cover seals and protects the lamp within the reflector. And there you have it. Well, that went by in a flash. So, whether you're after a good return on your investment or looking to purchase something to entertain in the summer months, or perhaps you're just a big kid after a big boy's toy, now you know how it's made. Today on How It's Made. Wooden bowls. We're dishing out the details. Chainsaws. We'll show you how they make the cut. Stackable potato chips. We go to the factory where the inventory is piling up. And jet compressor blades. An idea that's really taken off. But first, there was a time when bowl making was a cherished trade, passed down through generations of families. But today, with so many inexpensive materials with which to mass-produce tableware, handcrafted wooden bowls have become a speciality item. And this centuries-old traditional craft is almost a lost art. These exquisite bowls are made from a solid piece of hardwood, beech, maple, walnut or cherry. Logs arrive at the mill fresh from the forest, so they're still damp. There's an advantage though, because the moisture lubricates the cutting tools. The first step is to divide it into blocks. The chainsaw operator measures and inspects the log. the length of each block is determined by the diameter and defects such as knots or scarring. He inspects the ends of the block, marking any cracks or other flaws with a red crayon. The ripsaw operator uses different size bowl patterns to determine the best way to cut the block. The goal is to get the most and biggest bowl-sized pieces possible without using the defective areas. Each piece is called a bowl blank. This block is large enough to yield 3 blanks. Each one is wide enough to produce a 43 centimeter bowl and a series of progressively smaller bowls that nest inside it. They mount the blank on a specially designed woodworking lathe. From this point on, everything depends on the skilled hands of the lathe operator. As the block spins, he carves out the bowls using a series of specialized knives. First, he uses this curved knife to shear off the outer portion. It takes great expertise to know exactly how to angle the tool and when to pull it out to release the wood shavings and prevent a jam. After 2 or 3 minutes, what they call the exterior bark shell has been removed. The bare wood that's left will be the outside of the largest bowl. With a finer blade, he now sculpts the wood to just the right thickness and smooths the surface. Now he switches to a smaller curved knife and cuts into the wood. This both forms the inside of the largest bowl and the outside of the next smaller one. He repeats the smoothing and cutting process with progressively smaller knives, making bowl after bowl at a rate of about 1 a minute. This one bowl blank produces 4 nested bowls, the smallest measuring 23 centimeters in diameter. The bowls are steamed for 4 hours to draw out the sap and penetrate the pores of the wood, hydrating each bowl, preventing cracks and splits while air drying. Once a bowl is dry, about a month later, workers even out the top rim on a sanding table. Then using a belt sander, they smooth the outside and inside surfaces. The bowl now goes upside down through a specialized knife that shaves off part of the bottom. This gives the bowl a flat base on which to sit and a place to inscribe the company name. Businesses can order custom-made bowls featuring their company logo. Artists burn the design onto the wood or paint it on, or do a combination of both. The bowls now go for a bath in a non-toxic mineral oil. This nourishes the wood, preventing dryness and cracks. Oiling also brings out the natural beauty of the wood grain. And because every raw log is unique, each dish will really bowl you over. It's loud, it's powerful, and it rules the forest. The chainsaw has revolutionized the logging industry by replacing mortal muscle with mechanical torque. It's made the work a whole lot easier, so it continues to be a rip-roaring success. The chainsaw can set up any tree for a big fall, and then chop it up. These machines start with the plastic housing. 3 aluminium inserts will be molded into it to provide solid anchors to attach other parts. A robot picks up the inserts one at a time and delivers them to an injection molding machine. The robot strategically places the inserts in a mold at the front of the machine. The machine then injects molten plastic into the mold to make the chainsaw's engine cover. During the molding, the metal inserts become integrated into the housing. It takes just seconds to transform these plastic pellets into a chainsaw engine cover. The robot carries each engine cover to automated cutters that remove any unwanted plastic. The scrap drops into a bin below. A robot then places each engine cover in a special fixture to cool for about 10 minutes. Then it moves the part to the next station. There's one more piece of plastic housing, the fuel tank. This sonic welder melts and fuses it to the engine cover using high-frequency vibration. Now they move to the engine and install a spring system for the starter cord. They slide the two-stroke engine into the plastic casing and insert a spark plug. They lubricate the crankshaft, then install an automatic oiling system for the saw chain. The carburetor is attached, and then the starter system with the pull cord handle. The air filter is fitted into its slot. Then stud bolts for the chain bar are dipped in adhesive and screwed into the inserts molded into the plastic housing. They attach the rear handle and a trigger with a safety release. Then they screw the front handle into place. A filter is attached to the oil line that lubricates the bar and chain. It will strain out any impurities. Now they install bearings and the clutch system on the crankshaft. The clutch is the link between the engine and the chain. When it's engaged, the chain moves around the cutting bar. The engine is ready for a test run at a typical speed of 8,000 RPM. They adjust the carburetor so that it mixes the right amount of fuel and air, and check the exhaust to make sure it doesn't exceed pollution laws. They attach the trademark sticker and other operational information. Then they attach a brake system. Finally, they pack the metal bar and chain blade in a protective sleeve. Once the operator installs the chain blade, he has a power tool with teeth for any job. That's one clever fella. Coming up on How It's Made, special crisps that you can stack neatly. And clever bits of kit to keep you in the air. See you after the break. Welcome back to How It's Made. Each stackable crisp is made exactly the same, unlike others that come in irregular shapes and sizes. This uniform concave shape allows the crisps to tightly interlock, so you can fit a lot of them in a tubular container. It's a snack that's made to stack. Whether you call them chips or crisps, this is a case of production going down the tubes. To make these tubes, big rolls of plain brown paper and foil-backed paper unwind. The foil will help keep the crisps fresh. The streams of paper travel across rollers that coat them with glue. The paper layers twist around a mandrel that's turned by a belt. The belt also presses the glued layers together. Next, the label paper gets a coat of glue. This helps it stick to the paper on the mandrel. A camera photographs the white edging on the label paper, then relays its location to a set of circular knives. They make a precise cut below the white edging. After each cut, the carriage moves the knives into position for the next one, cued by the camera. These paper and foil tubes head into a turning station. It's a box with a pathway inside that turns the tubes right side up. Hot metal heads curl the tops to allow lids to fit on. A roller pulls foil-backed paper into a cutter that punches out the lid shapes. Small vacuums take the lids to the tubes and heat seal them on. Plastic lids go over the paper ones. The lidded tubes are now turned upside down. They're ready to be stacked with chips. They use a ratio of 1/3 water to 2/3 potato flakes, with a little cornstarch mixed in. A conveyor delivers the mix to an auger, which dispenses it. Then it falls between the rollers. Using 4 tons of pressure, they roll the mix into one long potato sheet. The potato sheet goes under a rotary cutter that punches out oval shapes. A device pulls away the scrap dough, leaving flat, uncooked crisps. This scrap dough goes back into the operation, while the crisps head into a fryer. As they travel through the fryer, rolling molds make them concave. The concave shape makes the crisps stackable. They spend 11 seconds frying in hot oil. This makes them crispy. They travel under blowers to get rid of excess oil. They then get a coat of seasoning and flip off one conveyor and onto another, falling in neat piles. A worker inspects the rows of crisps. Then, it's onto another conveyor that shakes them to loosen the pack. They travel over scales to portion them out for packaging. Automated spoons feed the crisps into the open ends of the tubes. Guides tap the top of the tubes to nudge the crisps into position. Grippers then lower the stacked tubes to a station, where spinning heads force metal bottoms onto them. Now they're ready for shipping. It takes about 20 minutes to make a tube of stackable chips, quite a lot longer than it takes me to empty them. Compressor blades are key components in a jet's engine. Thousands of them rotate 400 times per second, whipping air into small hurricanes. They compress the air, making it so hot and dense that it literally explodes when mixed with fuel in the combustion chamber. In a jet engine, large compressor blades made of titanium compress the air entering the front of the turbo chamber. They move the air toward the back of the chamber, where smaller blades made of nickel alloy compress it even more. The air heats up to more than 600 degrees Celsius that combines with jet fuel, creating a powerful mix that produces the thrust. The blades start off as metal pellets called slugs. A ceramic layer prevents their surface from oxidizing when exposed to intense heat. The slugs are heated for 15 minutes in a 980 degrees Celsius oven. Meanwhile, a robot sprays lubricant on two forming dies inside a press. The robot retrieves the slugs and loads them into the first die. The press applies 1,000 metric tons of pressure to preform the metal. The robot then transfers the slugs to the second die, where they take the initial shape of the blade. The blades are then dipped in water to cool. The next robot cleans the metal burrs off the edges. The blade is now an aerofoil. Robots will shape the rounded base of the blade, called the dovetail, later. The aerofoil has gone from this to this. After a new ceramic layer is applied, the blade is once again heated in a convection oven to 980 degrees Celsius. Each heating and cooling cycle tempers the metal, making it more resilient. 1,600 metric tons of pressure gives the aerofoil its final shape. A trimmer shaves off the excess metal. The heat has turned the protective ceramic layer into glass. It'll later be removed. It's taken an hour to shape the blade's aerofoil. The dovetail, the knob on the right, is next. But first, this measuring machine inspects the aerofoil. If any measurement is off by just half the thickness of a human hair, the blade is rejected. The casting machine will encase the aerofoil in a matrix, a coating that protects the aerofoil during work on the dovetail. They mold the matrix from liquid tin and bismuth. It solidifies into a metal cast around the aerofoil. The future dovetail sticks out at the end. They load the cast into what's called a broach machine, with a series of teeth that carve the dovetail to its final shape. Now the cast can come off. A worker loads it onto the removal machine. A hydraulic cylinder hits the cast at its weakest point, breaking it in half. The finished aerofoil emerges unscathed. A dot matrix machine punches identification numbers onto the blade. Next, they submerge the blades in fluid that penetrates any flaws in the metal. This inspection is critical because even the tiniest nick can spell disaster. They examine the blades using ultraviolet light. This blade is perfect. But spots of fluorescence on this one indicate microscopic cracks and weaknesses. The dovetail gets 2 strips of rubber silicone that ensure an airtight seal when the dovetail slides into its slot on the compressor drum. A final check, and the blades are now ready for takeoff. So, whether you're looking for something dishy that'll really bowl you over, or after a slice of cutting-edge technology, or perhaps you just want to stack up on those carbs, now you know. how it's made. Today on How It's Made. Steel wool. When it comes to cleaning, this can be your best alloy. Cookers. We have all the elements of this manufacturing process. Carved candles. We'll be waxing lyrical about this one. And slot machines. We bet you'll love this story. But first, mechanics were the first to use steel shavings to polish things. But by the early part of the 20th century, equipment was invented to mass-produce steel wool. It has lots of rough edges, so it's very abrasive. But that is what we love about it. There are thousands of metal threads in each steel wool pad. To make it, they start with coiled steel rod that unwinds through metal guides into a 5-meter-long die machine. It pulls the rod through 6 progressively smaller dies to narrow it and make it uniform. Spools wind up the rod after it passes through each die to prevent any snarls in production. The repeated drawing through dies reworks the steel's basic structure, doubling its tensile strength. When it reaches the end of the die machine, the diameter of the steel rod has been halved. This slimmer, stronger wire will be easier to process. To double-check its tensile strength, a sample piece of wire is placed in a testing device. Clamps pull it from both directions. It takes over half a ton of force to snap it, an indication that it's strong enough to be machined. So it's over to the steel wool cutting machine, which spans 15 meters. Here, the wire travels over a series of drums, while 29 blades shave it. Each blade produces shavings thinner than a human hair. Streams of the shavings exit the machine. They make a quick turn around metal guides to merge with others. Each of these steel threads has been cut in a pyramid configuration, which makes it razor sharp. The steel threads wind en masse onto large rolls under the machine, accumulating in one big pack. Next, they align several of the rolls of steel wool on racks and then secure them in place. They pull fibers from each roll and bunch them together. Then they thread the bunched up ends through a series of bobbins. They feed the ends of all the rolls of wire to a needle punch machine. Here, hundreds of needles, shaped like fish hooks, weave all the steel threads together and turn it into wool. It's a very basic crochet job, and it produces a long mat of wool that's a suitable density for woodworking. To make household cleaning pads, they bulk up the steel wool even more. They insert layers of needle mat into the streams of steel fibres. This gives it extra strength, suitable for big cleaning jobs. The double-layered stream then heads over to the needle punch machine to be woven together. Once the wool goes onto a final roll, it's wired and ready to be turned into pads for cleaning, sanding or polishing. Jobs for which its coarseness will definitely be appreciated. Still haven't seen any steel sheep though. A couple of centuries ago, cooking was mainly done in cauldrons over fires. We've certainly developed a taste for something a lot more civilized. The cooker is where the action is in the kitchen. It's where we whip together meals. And perhaps discover our inner chef. High-end cookers like this one are hot. And not just in the obvious way. They're an upmarket trend, because cooking with one of these is an experience to savour. To make one of these double oven cookers, they start with a big sheet of galvanised steel. A machine flips it and feeds it to a press. The press folds the sheet twice to make walls for an oven, closing it around the framework. They position the oven bottom on the 3 walls. Automated welders fuse everything together. The back section goes on next. The oven shell gets a porcelain finish on the inside. Those holes are for the oven fans. And they install elements on the bottom of the ovens. Fans are placed over the pre-cut holes. More heating elements run along the perimeter of the fans. They lower the oven and wrap it with synthetic insulation. Side panels cover the insulation and help support the oven structure. This piece of steel will reinforce the base of the cooker. They fasten feet to it. The front ones have wheels, so the cooker can be moved without tearing up the floor. They cushion it with packing foam, flip it, and hoist the oven onto the base next to a smaller second oven that's part of this double oven cooker. Then they hook up the microprocessor board that controls everything from the fans to the timers on both ovens. They plug it in and test the wiring to make sure it all works. This is a dual fuel cooker. The burners are fired by gas. This electrical board will sense gas flow problems. They assemble the igniter boxes that produce the spark to ignite the gas-fueled burners. They mount the igniter box assemblies on the cooktop. They install the gas valves on the framework. And then slide connectors onto the gas lines and attach them to the valves. On this top-of-the-range cooker, there are 2 gas lines for every knob, one for a low flame and the other for a high flame. They install the burners and a porcelain drip pan. The top is now ready to be lowered onto the ovens. This part will hold the knobs. It's called a bullnose, and it's a showpiece. So they grind and polish it to give it a gleaming finish with no sharp edges. For handling purposes, they protect it with plastic. This machine punches and bends the edges of panels so they can attach them to the sides of the cooker. At another station, they buff up the doors of the ovens so they'll match the shiny bullnose. After all, when you're making a meal, presentation is everything. With the side panels and doors attached, all that's left are a few more finishing touches. And the final product is truly a feast for the eyes. Coming up on how it's made, we shed light on candle making. And then gamble on taking a look at the slot machine. See you after the break. Carving candles is an ancient craft. It involves layering different coloured waxes and then carving designs that expose those colours and the luminous core. It's hard to beat the radiant beauty of a carved candle, but we'll try not to wax lyrical about it. Carved candles are known for their swirls and curls, a look so elaborate that lighting one is in itself an occasion. They start with vats of hot wax in various colours. The candle maker stirs them to circulate the specially formulated dyes. She dips a star-shaped wax core into clear wax and then yellow. The clear wax dilutes and lightens the yellow. She hardens the layers in cool water. She repeats this process between 30 and 35 times as she builds up layers of different coloured waxes on the candle core. As the dipping continues, the candle becomes warmer and softer, which will allow it to be carved. The quick dips in water only cool the outer layers. Part-way into the dipping, she deepens the grooves in the candle. She resumes dipping and keeps a close watch on the temperature of the water and the wax. If the candle absorbs too much heat, it will become too soft to carve. But if it's too cool, it becomes too rigid to carve. Achieving the right consistency is crucial. It's almost time to carve. But first, she squeezes the drippings together and then slices them off. These multicoloured drippings are too attractive to waste, so she shapes them into a mushroom candle. She pokes a hole in the centre for the wick. She has just 15 minutes to carve the main candle, or it will be too hard to work with. She slivers the bottom and curls the pieces back. It peels back the layers of colour for an eye-catching display. She dunks the row of curls in water to harden them a bit, so they won't sag. Here's a twist. She curls each row in the opposite direction to the one before. She carves a total of 4 rows and curls the last slivers up rather than down. Using a square-edged gouging tool, she cuts a windmill design into the upper section of the candle. Then, she shapes the wax cutouts into a deck for the windmill. She carves tulips and other designs around the top. She works quickly and with a steady hand. It takes at least a year of training to learn to carve and shape these designs so quickly. This one's a neat trick. She jiggles a straight-bladed knife to cut the fluted edge of a hummingbird wing. One last character and this carving job is complete. Now she presses a device that's a bit like a pastry cutter around the wick. This forms a well that will allow the candle to burn down the centre instead of dripping down the sides, which would ruin the carving. She spins it in a hot pan to melt the bottom so that it's level. And while it's still hot, she presses the trademark sticker onto it. Finally, she dips it in an acrylic glaze. This seals everything to the candle and protects the finish. Once lit, the light from the clear core shines through the designs for real glowing beauty. A San Francisco car mechanic invented the first slot machine in 1895. 3 mechanically spinning reels had 20 playing card symbols and an image of Philadelphia's famous Liberty Bell. If you were lucky enough to line up 3 bells in a row, you won the mighty jackpot of 50 cents. Bingo! Today's slot machines are glitzy and high-tech. They've got computers for brains and endless game themes and configurations, all packaged in cabinets made of lightweight sheet metal. Workers first assemble what's called the bulkhead, the upper part of the cabinet that contains all the game-playing components, such as the audio amplifier, the circuit boards, the speakers, and what's known as the meter, the electromechanical counter that keeps track of the coins and credit going in and out of the machine. At the base of the cabinet, they engrave the machine's serial number, required by law. Workers install the machine's bill acceptor, into which you insert paper money, then the ticket printer. When you win, it spits out a ticket to either cash in or feed in to continue playing. They hook up the arm mechanism you pull to spin the reels. Then the upper door that frames the reels. Then the lower door that frames the button panel. Slot machines have several illuminated buttons for different types of bets. Workers plug a tiny LED behind each button, then wire up the panel. A plastic insert labels each button. Once they finish assembling the panel, they install it in the lower door. Now they take a metal panel with windows for the spinning reels. On the back, they install 2 circuit boards, one to operate the machine's digital scoreboard, the other to illuminate the reels. They cover it in glass treated with a chemical that conducts electricity. Should a player try to rig the reels using an electronic gadget, this glass will earth the signal. A decorative window goes over the anti-tampering glass. Then workers install the whole shebang into the upper door. In the lower door, They install a touchscreen video monitor to display the payout information. Casino technicians also use it to configure the machine. Then workers install panels with slots for receiving tickets and for inserting either money or debit cards. And now for the slot machine's most famous feature, the reels. After a machine tests the spinning motion and lights, a worker slots in a plastic strip with printed symbols, 18 to 22 symbols per reel. The reels just snap into place into a waiting electrical connection. Next comes what's called the top box. Workers mount it onto the bulkhead, then install fluorescent bulbs. These will light up the eye-catching artwork on the glass front of the box. With a fully developed body, the slot machine is finally ready to receive its brain, an operating system on a programmable microchip in the machine's internal computer. The software that runs the game is on a memory card. It randomly determines the course of play, but within defined parameters. Essentially, it's pre-programmed to pay out a certain amount at random intervals over a period of time. But less money, of course, than the machine takes in overall. Before embarking on its spinning spree, each and every slot machine undergoes extensive quality control testing. Casinos demand the reliability of these one-armed bandits to be a sure bet, because slots generate more than 2/3 of casinos' revenues. Profits they won't want to gamble with. So, whether you're looking for something with the metal to do the job, or you can stand the heat and you want to stay in the kitchen, or perhaps you don't want to burn it at both ends, you just want to admire its beauty. Now you know how it's made. Today on How It's Made. CCD Semiconductors, making your digital photos picture perfect. Airline meals, when they make them, believe us, they aren't just winging it. Paper cups, we pay lip service to the manufacturing process. And trumpets, we visit a factory that likes to blow its own. But first, a CCD semiconductor is the image sensor in a digital camera. When you snap the shutter, you expose the CCD to patterns of light, which are recorded electronically. The camera's processor then translates them into the image you photographed. CCDs, or charge-coupled devices, are made of silicon, the main element in sand. Well, what's special about silicon? When light hits it, you get electrons. Production begins with a round silicon wafer 15 centimeters wide. It goes into a steam oven for 3 to 4 hours. The intense heat along with the oxygen and hydrogen gases in the steam create a glass-like layer on the wafer. This insulates the silicon against the miniature electrical circuitry they'll build onto it. But before making that circuitry, they cover the wafer in conductive material. This conductive layer measures less than a micron. A human hair is 100 times thicker. Onto that, a robot applies a 1 micron thick layer of photosensitive resin. When exposed to light, the resin will undergo a chemical reaction. A technician suspends a mask over the wafer. The pattern on this mask is the template for part of the circuitry. When you take a picture, you expose the silicon wafer to light and that generates electrons. The circuitry carries those electrons to the camera's processor, which reads the charges and translates them into an image. This machine exposes the masked wafer to ultraviolet light. The resin shielded by the lines of the circuitry pattern remains intact, protecting the conductive layer beneath it. The resin on the areas not masked by the circuitry pattern breaks down and becomes vulnerable to specific chemicals. The next step is to spray the wafer with those chemicals. This dissolves the resin, exposing the conductive layer underneath. Technicians repeat this entire process with anywhere from 13 to 30 masks until they've built up the full circuitry pattern on the wafer. Next, technicians submerge the wafer in acid, which eats away the uncovered conductive layer. So now the only conductive material left on the wafer is the actual circuitry, the unexposed resin coating having shielded it from the acid. Next step, a thorough rinsing in ordinary tap water to remove the residue. Then a rinse with purified water to remove any impurities left by the tap water. Throughout production, contamination is a concern. Just a single speck of dust can ruin a wafer. To protect and insulate the circuitry, they coat the wafer in liquid glass, then bake it for 2 hours until the glass solidifies. The wafer surface is divided into 25 million tiny square cells called pixels. When you take a photo, each pixel records the light intensity of a minute portion of the scene, generating an electrical charge. A filter on the CCD translates each pixel charge into color. The company makes this filter with 3 pigment powders, red, green and blue. These 3 colors combined can reproduce any color. The camera's processor reads and then reconstructs the photographed scene pixel by pixel. Each finished CCD undergoes a battery of automated tests to ensure that all the circuits are functional. This machine marks faulty circuits with ink. Just one bad circuit is enough to discard the entire CCD. Technicians then check every CCD under a microscope, looking for scratches that might have occurred during the production process. This is a 25 megapixel CCD. The number of pixels varies depending on what type of camera it's for. This company even produces a single CCD that has 111 megapixels. So, the next time you say cheese, remember that you're producing a digital photo thanks to all that painstaking work that went into the sophisticated CCD semiconductor inside your camera. Smile, please. In the earliest days of air travel, passengers really lived the high life. There were multi-course meals that were actually prepared during the flight. But as air travel increased, this became impractical, and airlines turned to pre-made meals. Because when you're feeding a lot of people in a small space, it's best not to leave dinner up in the air. These are meals meant for a higher purpose, as in feeding folks at an altitude of thousands of meters. That's why you don't see any soufflés here. They couldn't possibly rise to the occasion. It's just one of the things they consider when preparing airline meals. Airline meals start with a load of ingredients. They make 45,000 meals at a central facility in one day. As with any food preparation, good hygiene is essential. They cook on grills that are 1.5 meters long. At one end, they stir-fry a big batch of vegetables, while at the other, they sauté potatoes. They spice it up. Airline food isn't really all that bland, but the atmosphere on the plane may affect our perception of it. It's believed that low humidity and the pressurized environment cause our taste buds to work less efficiently, something to take into account when you're traveling. The recipes also vary according to the route. Flights to more exotic locales will offer spicier dishes, while a domestic North American flight usually calls for a little less seasoning. They fire up different grills for the meat. They're making meals for the crew as well as the passengers. On many airlines, a pilot must eat a different meal than his counterpart to minimize the risk of food-related illnesses compromising the flight. The cooked food will now be blast chilled in special fridges. They scrub up again as they prepare to assemble the meals. They start with the food that's to be reheated on the plane. It goes into foil containers. Smaller containers inside help to control the portion sizes. They're careful not to overfill them, to avoid spillage. Some sauce and a generous dab of butter, and you have the makings of a first-class meal. They put the lids on and make sure to vent them. With each menu change, the chefs meet with airline representatives. They serve up sample dishes and discuss the ingredients with them. There's often a lot of negotiation before a menu is settled on. Every detail is planned right down to the plates and bowls, and how they're going to be arranged on the serving tray. It takes a bit of arranging to make everything fit. Once they come up with a spot for everything, they follow that formula in the kitchen. As with any meal, presentation counts for a lot. Of course, meals for passengers in the economy section are more simple, and the planning less detailed. The food-laden trays all go onto trolleys, and then they roll them into a big refrigerated room where they're arranged according to the flight number. They won't be here for long because every meal is made to be served that day. And all the groundwork is sure to pay off once the passengers are in flight, because this is food of high quality. Coming up on How It's Made, the paper cup for people who know how to hold their drink. And trumpets, an interesting story we got wind of. See you after the break. Welcome back to How It's Made. The paper cup was invented around the turn of the 20th century to stop the spread of disease. It's a hygienic way to quench your thirst or to get your morning cuppa. The lining of plastic or wax keeps it watertight, preventing any nasty leaks. And this concept continues to hold water. Anyone for coffee? With paper cups, you can have it and go. They start with paper that has a thin plastic coating. It unrolls into a printer that's as long as a bowling lane. The paper weaves through the printer in a continuous ribbon, as printing cylinders at each station layer an image onto the paper, one colour at a time. When the image is complete, a rotary die cuts the paper into a flat. The dimensions of the flat vary depending on the size of the cup being made. Each flat will eventually be a paper cup. They land on a conveyor. A computerized system counts the flats and divides them into stacks of 200. The flats drop into an elevator stacker. It piles them one on top of the other, so they can be easily collected by workers. They load them into another conveyor in a different part of the factory. It moves the flats in a vibrating shuffle up into the cup machine. Meanwhile, a roll of paper winds into the other side of that machine, where a die punches out bottoms for the paper cups. This leaves a long strip of scrap paper, which gets sucked away for recycling. A device grabs the flats and relays them to a carousel. Now the paper cup takes shape. Mechanical jaws wrap each flat around a mandrel, and a heat gun seals the seam. And now you have a paper cup with no bottom. Its life will surely be empty without one, so that goes on next. Bottoms are shoved into the cups and heat sealed in place by melting the plastic backing on the unprinted side of the paper. Then cups fall down a chute to the next operation. This one will give the cups a rim, allowing you to take a sip without spilling. A hot tool curls the edge of each cup into a rim. Then a vacuum sucks each cup into ductwork overhead. Each piece of ductwork comes from a different production line. There are big cups and small cups, all travelling to the packing department, where they land in stacking tubes. A counter keeps a running tally on the paper cups and portions them out. The stacks of cups slide into a curtain of plastic. Hot jaws seal the plastic wrap around the stack. So now they're stacked, wrapped, and ready to be packed. Meanwhile, over in the testing department, the kettle is on, but this is no coffee break. They've pulled some cups off the production line to check for leaks. A mirror below reflects the situation. But leaks are 1 in a million, so they've made one leak deliberately to demonstrate for our camera. In the case of a real leak, they stop production and follow the paper trail, so to speak, until they determine the problem. It takes about a minute to transform pieces of paper into a cup. So, whether it's for mineral water, latte, or a drop of Earl Grey, the paper cup, there's so much in it. The ancestor of the modern trumpet was a straight horn that could emit just a few notes. By the 15th century, they learned how to bend the horn, increasing the length of the instrument and the series of notes it produced. The invention of the valve in the mid-1800s finally allowed the trumpet to be played in any key. A trumpet is made up of 1.5 meters of tubing. 3 valves allow air to flow through additional tubing to alter the trumpet's pitch. Trumpets are made from sheets of metal, most often brass. This factory combines different thicknesses in a single instrument to attain a particular sound. Workers first lay a template on a brass sheet and trace it out. They then cut along the score line with electric shears. This piece will become the trumpet's bell. A manually operated press forms a perfect fold down the middle. Then they notch the edges. Then they close up the bell by hammering the notched pieces into the opposite edge. They use a rawhide mallet because anything harder would damage the brass. They melt a brass alloy along the joint. It solidifies into a metal seam that bonds the edges permanently. They slip the bell over a cone-shaped mandrel and hammer the brass until it too is cone-shaped. Then the bell goes onto another mandrel mounted on a lathe. They push the brass against the mandrel to finalize the shape. Then they file the metal smooth. Now for the bell's rim, called the bead. A brass rod with a notch at the end catches the edge of the bell and rolls it back into a rim. They use what's called a concave roller to round the rim's jagged edge. Then they slide a brass alloy wire into the rim pocket. This makes the bell stronger and adds weight to the edge of the flare to project sound better. They roll the rim over even more to enclose the wire. Now they heat the rim and apply acid flux to clean the surface for soldering. Lead or silver solder ensures the wire won't rattle when the bell vibrates. After wiping off the excess flux, they put the bell back on the lathe and scrape off the excess solder. Using an abrasive sponge, they smooth away any scratches left by the scraper. Then they remove any solder bits trapped in the rim. Now they'll fill the entire bell with a soap and water solution, then freeze it at -49 degrees Celsius. When the water has frozen, they place the bell in a bending block. The ice provides counter-pressure, preventing the brass from buckling inward. The ice itself doesn't shatter under the pressure because the soap in the water makes it pliable. After checking the angle of the bend with a gauge, they let the bell defrost. In the mounting department, workers assemble smaller components made of brass and nickel, valve casings, the sliding tubes to which they connect, the slide for tuning the trumpet, and the pipe that holds the mouthpiece. Then they solder on the bell. They lubricate 3 pistons and install 1 in each valve casing. These slides have to fit loosely enough to move freely, but tightly enough to prevent air leaks. 1 slide has a finger ring for holding the trumpet. After polishing and lacquering the brass, they test the trumpet for sound quality. This is one company that likes to blow its own horn. So, whether you're after a clever little gadget to improve your image, or perhaps you think high tea is a flight of fancy, or you're a coffee buff that doesn't want to be taken for a mug, now you know how it's made. Today on How It's Made. Padlocks, a device that makes us all feel more secure. Hair clippers, we have the buzz from the factory. Wooden shoes, clogging your feet, not your arteries. And synthetic leather, a matter of know-how and no cow. But first, as long as there have been thieves, there's been a need for locks. Padlocks date back to Roman times and were likely first used as cargo locks to protect merchandise. Thousands of years later, the padlock continues to keep burglars at bay. The modern padlock's strongest point is its laminated lock body. To make it, they stack 24 steel plates like these and then laminate them together. It's the same technology that's used to make doors for bank vaults. A punch press cuts and shapes pieces of steel into caps. They'll be riveted to the lock bodies. The rivets tumble down a feeder, while below an operator places a lock body in a fixture and places a cap on it. A powerful press drives them into the assembly, securing the top cap to the lock body. At another station, cutters machine steel rods. They contour them so they'll fit into the holes of the lock body, while lubricant keeps things cool. They load the rods into a form press. It bends the steel to make a U-shaped shackle. Then the shackles roll into a furnace for tempering, which will toughen them up. After a little more machining, the shackle is ready to be installed. The shackle will need to move up and down as the lock is opened and closed, and that's where these ball bearings come in. They install two in the lock cavity. These bearings will work with the cylinder extension to open and close the shackle. Lubricant gel aids the process. They use it to grease the inside of the lock, while at the same time pushing the ball bearings to either side of it. The cylinder extension goes between the ball bearings. Then they slide a protective casing and bumper over the lock. Now they assemble the locks. A machine loads copper-plated shells onto mandrels. Plugs, pins and springs funnel into the lock assembly station. A device installs pins and springs in a lock shell. The shell slides onto a brass plug. This plug has a groove cut into it that matches a key. A carbide cutter notches the keys. There are tens of thousands of key profiles. This sorting station holds just a few. The keys and lock cylinders are all numbered accordingly. This worker matches them up, making sure there are two keys for each lock. She selects a padlock and pushes one of the lock cylinders into it. It's time to top it off with a retention plate. A machine press fits it to the bottom of the padlock. This secures the lock cylinder. They install a spring for the shackle, and the bottom cap goes on next. Then the entire assembly is riveted together. They try the key to make sure it matches. a computerized system opens and closes a randomly selected padlock thousands of times to make sure it's up to the job. Finally, they try to bust the lock on purpose. They drop weights to replicate the force of a hammer, and the padlock withstands the blow. This day's work is done, and it's time for the folks at the factory to lock up for the day. The invention of the electric hair clipper in 1919 was sheer progress. It was the first clipper with a motor in the actual unit, allowing the barber to cut hair at a very steady clip. Hairstyles change, but the electric clipper motors along, always at the cutting edge. Hair is definitely a growth industry, so these early electric hair clippers were an easy sell. These days, they make the casing for hair clippers out of heavy-duty plastic. An automated mold melts and shapes the plastic material into casing parts. A robot picks up brass contacts and places them in fixtures. Another robot then attaches a plastic switch to each contact. A blast of air sends the assembled piece to a bin. Here, a robot slides a plastic spool onto a mandrel, then anchors copper wire to it. They wind the wire around the spool more than 2,000 times to make part of the electric relay that will drive the blades. Pulleys keep the wire feed at an even tension. Next, robots work on the clipper's lower casing. One installs a blade slide for adjusting the blade, and another picks up a lever to engage the slide. The robot attaches the lever to the case and blade slide. And an automated screwdriver fastens everything together. Another robot then sends the clipper assembly on its way to have a metal arm placed inside. It will move the cutting blade, and for that, it will need a couple of springs. They slide the switch assembly into position. Then they screw the arm into place. They install a screw for adjusting the power setting. And now they fit the copper wire coil in the lower housing, where it will drive that metal arm. To activate it with the flick of a switch, they run a power cord from the switch to the coil. Over at another station, a punch press stamps out blades for the clippers. The blades are toothless to start. They're not yet sharp enough to cut it in the barbershop. So after a good wash and heat treatment, they head over to another station to get some teeth. A worker pops a blade into a fixture to hold it steady, while a jagged cylindrical cutter carves the teeth. Coolant keeps things from heating up and compromising the integrity of the steel as the cutter does its work. Each hair clipper has two blades, one with cutting teeth that moves over a larger stationary blade, which ensnares the hairs so they can be cut. Next, they print the company logo on the clipper's lid. And they attach the lid to the casing that holds the electrical components. They mount the blades on the head of the clipper for that double-edged cutting action. And finally, They tune each clipper for optimum performance by adjusting that power screw installed earlier. The clippers come in a kit. This one will be sold for consumer use, for those who want to try their hand at a little home grooming. Now, these electric hair clippers are ready to make any bad hair day better. And with those toothy blades, they'll definitely make short work of any hair challenge. Coming up on How It's Made. Wooden shoes, a treat for your feet. And synthetic leather, not real, but really clever. See you after the break. Welcome back to How It's Made. Centuries ago, workers chipped out holes in wooden blocks to keep their feet dry. Now people still wear wooden shoes, but for different reasons. And while they may look slightly more glamorous, how they're made remains as basic as the shoe itself. Most wooden shoes are made of poplar, easy to carve and generally free of knots, so it makes wearing clogs a splinter-less experience. A worker feeds sticks of poplar into a bandsaw, careful to toss any pieces with defects. The blade slices the wood into blocks called blanks. The factory uses vinyl patterns like this one to create the shape of the shoe. There's a pattern for each size of every clog style. A worker locks one onto a duplication machine called the shaper. Then right next to it, 2 blanks. This tracer moves over the shape of the pattern. The wheel on the left copies the tracer's movements exactly. Its blades shaving the wood as it moves up and down. There's only one pattern loaded, yet the machine carves out a pair of shoes. That's because the blocks of wood spin in opposite directions, while the blades chip away at them, essentially creating mirror image copies. That allows the machine to carve out both a right and left shoe simultaneously. Now for the instep. A worker positions the blanks onto what's called a dual-action boring machine. The center rod is called a tasker. Its rolling head follows the curves inside the pattern. The spoon bits on either side of it copy the tasker's movements, gradually carving out the inside of the shoes. Now they shift the angle so the spoon bits can get in deeper. They bore all the way to the front of the shoe. Then workers employ this very high-tech maneuver to remove all the wood chips. They lay the shoes on racks to dry out the wood, then cut off the knobs at the toe with a bandsaw, while inspecting for flaws that may have come out during the drying phase. A disc sander grinds down the knob on the heel and refines the shape of the toe. They work with a barrel sander to smooth out the opening, then switch to a balloon sander. The air-filled rubber sack inside flexes to the shape of the shoe as it sands. Now, for the final step. An artist lays carbon paper on the shoe and a pattern on top of that. Then she traces the pattern. The carbon sheet transfers the design to the wood. Now she goes over the design with a wood burner. She changes the tips and varies the temperature according to the size and depth of the lines and curves she burns. This design commemorates Holland, Michigan that is, in the United States. The artist now uses water-based paints to enhance the scene with colour. She applies 3 coats of a water-based varnish to preserve the artwork and help keep the shoes clean. While most clog-wearing workers opt for a plainer version, true clogaholics prefer a bit more pizzazz. But making them should be left to the experts, because they leave big shoes to fill. Is it leather or is it pleather? It can be hard to spot the fake. Synthetic leather or pleather can look and feel very much like real cowhide. It may not be the genuine article, but its growing popularity means it's become a bit of a cash cow. Plenty of good-looking products are made from synthetic leather. To make synthetic leather, they pump a petroleum-based plasticizer into a mixing tub. They add an ultraviolet light stabilizer to provide protection from the sun's rays. And they pour in a flame-retardant solution for fireproofing. As the mixer blends it together, they add powdered vinyl until the batch is about the consistency of pancake batter. Next, they pour different dyes into another tub, following a formula for a specific shade. They pipe the liquid vinyl into the tub with the colouring agents. Now, a large roll of paper with a leather-like texture to it unwinds into the coating machine. As tinted liquid vinyl flows into the machine, a mixing arm agitates the batch and rollers below apply it to the paper. The vinyl-coated paper then travels through an oven and the vinyl hardens, taking on the paper's texture. The first layer is only a thin one to establish the surface grain. A second batch of vinyl will contain a thickening agent. That's why they call it the foam. When applied to the first layer, it will give the fabric shape and structure. They pour the second vinyl concoction into the coating machine, and it rolls on top of the first one. The double-layered vinyl then travels through another oven, and the heat activates the thickening agent, causing the second layer to expand. Once the expanded vinyl has hardened and adheres to the first layer, they roll fabric backing onto it. A machine then peels away the paper to reveal the textured first layer. Sometimes they print a pattern onto the vinyl to make it look burnished or two-toned. Then they mix a solution to build up its durability. Rollers apply it to the synthetic leather, finishing off this production run. But hold on, it's not quite ready to be shipped out. Samples from every run undergo a battery of tests. This machine rubs the fabric up to 3 million times to see how it wears. Then there's a stretch test. They fasten a weight to a secured strip of synthetic leather. The weight pulls it to double its length, but it doesn't tear, which means this fabric has a lot of give. This test is a trial by fire. They hold a piece of synthetic leather over a flame and it catches light. To pass this test, the fabric must actually self-extinguish in 2 seconds. And it does, thanks to the flame retardants in the material. Next, they secure a piece in some framework and slide it into an oven to heat it to a more pliable state. A vacuum mold sucks the leather to its form, proving this fabric also has thermoplastic qualities. You can't do that with real leather. And because synthetic leather comes in many prints, textures and colours, it seems like it's got everything covered. So, whether you're looking for a product that gives you a little security, or you want to keep things neat and tidy, but you're tired of tipping your barber, or perhaps you're bored of leather and fancy something more substantial for your feet, now you know how it's made. Today on How It's Made. Racing shells. When it comes to making these boats, they're in it for the long haul. Stainless steel sinks. We plumb the depths of this story. Leather. We give you the facts behind that good-looking tan. And pedal steel guitars. We have all the key techniques. But first, rowing can be a lazy and leisurely pursuit, or it can be about fast and fierce competition. The racing shell is a rowing boat that's made for speed. Long and exceptionally narrow, it's designed to cut through wave drag and leave the competition in its wake. Racing shells are made for single rowers called scullers, for pairs or entire crews. They're custom made to precise specifications. Racers need to travel light to build up speed, so they make these boats from reinforced carbon fibre, which weighs a lot less than wood. They layer numerous carbon fibre sheets in a mould and trim them along the edge. They spray glue onto pieces of textured thermoplastic called honeycomb, then press it onto the carbon fibre. The honeycomb will serve as the core material for the boat. It will be sandwiched between layers of carbon fibre. It will give the racing shell some lightweight reinforcement. Next, they vacuum the air from between the layers, then wrap the entire boat in a big breather cloth and plastic bag. The breather cloth is a permeable layer that prevents the plastic from getting stuck on the mould, creating air pockets. Next, it goes into a long oven which melts the glue impregnated in the carbon material, fusing the layers together. After 8 hours at 99 degrees Celsius, all is revealed. They pull the plastic bag and breather cloth away from the shell. Then they pry the boat out of the mould using plastic wedges. The boat comes out in one solid piece, and a primer paint sprayed into the mould earlier has adhered to the outside. They check the weight, which has to be precisely what the customer ordered. Next, they reinforce the boat's cockpit with several bulkheads, all of which are made from carbon fibre. They glue foam on the inside rim of the racing shell, using a piece of wood as a guide. They bead glue around the bulkheads. Then they lower the cockpit panel so that it adheres to the glued areas. The hard foam installed along the edges support the cockpit. Next, using a computerized tool, they drill holes for the hardware and riggers, and they trim the rim from stern to bow. They smooth the finish using a grinding tool. And now it's over to the paint section for some sanding and priming. They look for flaws and mark them for repair, because any imperfection could affect the speed of the boat or the mindset of the racer. Once the boat is perfectly smooth, they spray on a high-gloss urethane. Next, they install a fin for some stability. Using a laser, they align the fin with a guide to precisely position it. They insert a rudder and attach it to a system of ropes used to steer. The boat comes with special shoes, along with a sliding seat that allows the racers to put some leg power into their rowing. Finally, they install the rigging equipment for the oars. With all the work put into these racing shells, rowers can't help but get ahead. Stroke! Stroke! The stainless steel sink is an invention born of patriotism. It evolved during World War II when sinks were often made of a copper-nickel material. When that material was needed by the war effort, stainless steel was drafted for use on the home front. And it was such a good alternative that it's still on clean-up duty. Stainless steel is lightweight and heavy-duty, which makes it great for sinks. To make one, they uncoil stainless steel into a shearing machine, where large scissors slice it into pieces called blanks. They place a blank under a 1,000-ton press. As it descends, a punch rises from below. It stretches the blank into a rough shape of a sink bowl. Stretching the steel also transforms the molecular structure, hardening it. Now they brush lubricant in and around the sink bowl to make it easier to stretch it again. The bowl goes under the same punch press, but this time it gets a more precise shaping. This second working of the steel hardens it even more. Now the sink goes under a different punch device. It cuts out a drain hole and forms a lip around it. Coolant flushes into the sink as an abrasive belt grinds the surface to give it a brushed look. They slide a sink bowl along rails into a welding machine. They butt a second sink bowl up against the first one in the welder. Inside, an electrode welds the two sinks together. Using enormous force, a roller moves across the seam to flatten it. A grinding belt behind the roller sands it down. The seam that joins the two sinks is now level and smooth. It's time to shape the rim of the sink. This die forms recesses along the sink's perimeter. The recesses give the sink a sleek look and collect water runoff. Another press trims the rim and gives it a bevel finish, which softens the rough edges. Now, using a punch cutter, they pierce the back rim of the sink to make holes for taps and a soap dispenser. It's time to scratch the surface as they grind and buff the sink to a fine finish. This process takes about 25 minutes. Using a hydraulic system, they emboss the trademark in a reverse configuration onto the outside of the sink, and it shows through in readable form on the inside. They block the drains of the sink with plugs and spray a substance similar to latex paint onto the outside. The finish will muffle the sound of dishes clattering inside, and it will also protect the sink from condensation. It takes about 2.5 hours to make a stainless steel sink, and now it's ready to go with the flow. Coming up on How It's Made. Leather. We couldn't hide from this one any longer. And pedal steel guitars. A production with strings attached. See you after the break. Welcome back to How It's Made. Leather has a rugged appeal that dates back to primitive times, when humans rubbed fats into animal skins to preserve them. Times have changed, but leather continues to endure. It's strong enough to take a lot of abuse, so it's a very tough act to follow. This leather comes from the hides of cows killed for meat. Without tanning, the cow hides would go to waste. Converting them to leather is kind of recycling. The first step is to cut each hide in half. They drape the hide over a sawhorse and then stamp an identification code onto it. They slice down the center. The two smaller pieces will be easier to handle and process than one large hide. They load hundreds of the hide sections into this modified cement mixer to undergo some serious hair removal. The mixer is filled with water as a worker dumps in a combination of sodium sulfhydrate and lime. A chemical reaction strips the hairs from the hides. They bathe the skins in acid to prime them to absorb tanning salts. The tanning happens inside big wooden drums with prongs that keep the skins from getting tangled during the process. The chrome salts turn the hides blue as they bind to the collagen fibers of the skins. This converts them to leather. They feed the leather, grain side up, to a machine that splits the leather into layers. It slices the leather on the flesh side to an even thickness. The cut-offs will be recycled into suede. They check each piece of leather with a gauge to confirm the thickness is uniform. Now it's into the wooden drums for a second tanning, but this time they use a solution of vegetable extract, tree bark and water. They add some dye and a chemical that will make the leather water resistant. The solution binds to the leather, giving it a brown tint. It's a gentler tanning than the earlier one, and it softens the leather. Now they brush a mix of starch and water onto the tanned hides. It's a kind of paste that allows them to press the hides onto big frames of glass, which have also been moistened with the same starchy solution. Pasting the hides on glass allows them to dry flat. Wipers clean the glass between hangings, and a spray system coats it again with the starchy paste. This method allows the hides to dry without shrinking and stops the ends from curling up. After 4 hours in a dryer, it's time to remove the hides. They easily peel away from the glass. A revolving paint gun system sprays the leather with dye to enhance the colour. And now it's time to create some friction. A glazing jack pulls a glass cylinder over the leather repeatedly, and the abrasive action polishes it. This glass is very strong, so it can do this vigorous work without breaking. Finally, huge heated rollers smooth out any wrinkles. It's the end of the production line for this big pile of leather. It will now be the stuff that many things are made of, and it's sure to live up to its tough image. It's quite a feat to play the pedal steel guitar. You have to slide a steel bar up and down the strings as you play them, while operating a system of pedals and knee levers below. This means using both hands, both feet, and both knees. It's a real performance. The pedal steel guitar has a unique sound and an impressive musical range. To make a custom one, the guitar maker carves the neck of the instrument from hardwood. He beads glue around the edges of the neck and applies strips of intricate wood inlay. Once the fretboard design is silk screened onto the top, the guitar neck is complete. He outlines a design onto aircraft-grade aluminium and cuts it out to make an end plate for the guitar frame. He pops the end plate out of the holding device. He welds it to the rest of the framework and polishes everything to a mirror finish. Next, he machines a part called the steps. These holes in the steps will be used to attach tuning pegs. He attaches the steps to the neck, just above the fretboard. This is the pickup plate. It will hold the pickup that transfers sound to the amplifier, as well as a series of metal fingers. To make those fingers, he machines several parts from aluminium and assembles them together. The fingers pivot to raise and lower the pitch of the strings. He fits all the fingers in the slot in the pickup plate and secures them with screws. He double-checks the movement of the fingers, then hooks springs to the end of each one to maintain the proper tension. A little grease ensures this next operation goes smoothly. He shapes a part called the cross shaft using a special cutter. Then he moves onto the guitar undercarriage to build a system that moves the fingers with foot pedals and knee levers. He screws several cross shafts, one for each pedal, into the undercarriage. He attaches bell cranks to the cross shafts. He connects thin steel rods to holes in the fingers and the bell cranks. This system will allow the performer to tighten or relax strings while playing. It's a kind of open tuning, and it's what gives the instrument its characteristic sound. He checks the knee lever to make sure it works. Here he's winding copper-coated wire around a cartridge thousands of times to make a pickup. He takes two of the wire-bound cartridges and places a magnet between them to complete a pickup. He fits it in the other slot in the pickup plate, just above the fingers. Now using a gauge and a level, he adjusts the pickup. It has to sit low enough in the slot that it won't interfere with the strings. The positioning must be exact, or the guitar won't sound right. He attaches 10 to 12 strings to the guitar neck. Some instruments have two necks, to add even more dimension to the sound. So now you have an instrument that's sure to steal the show. So, whether you're hoping to stay afloat and row, row, row your boat, or you feel all washed up and have that sinking feeling, or perhaps it's a natural tan you're after, now you know how it's made. Today on How It's Made. Swords. Making them is half the battle. Pontoons. We'll see what keeps this business afloat. Grandfather clocks. At this factory, time is money. And fuses. We'll have a blow-by-blow description of the manufacturing process. But first, for thousands of years, wars were won and lost by the sword. Swords help shape history. And although those days are gone, swords are not. Today, modern artisans craft historical replicas and they go to the hilt to get the details just right. This reproduction of a medieval sword is ready to capture your imagination and take you back to the days of knights in shining armour. To make one, they place a piece of high-carbon steel in a fixture. Computer-guided blades carve out the basic geometry of the sword that has all the specifications of the original. Centuries ago, a blacksmith would have done this painstaking job by hand, but with this machine, the job is no sweat, and the cut is much more consistent. After about an hour of carving, they have a tapered sword blank. They submerge it in hot liquid salt. It's a critical step. It softens the steel to eliminate stresses created by the carving. Next, they plunge the blade into containers of cool liquid in a process called quenching. It immediately hardens the edges of the sword, but the center cools more slowly. This allows the blade to retain flexibility, which will give the sword that springy quality. Using a belt grinder, they fine-tune the geometry of the blade and sharpen the edges. After that, it's sharp enough to slice paper to shreds. To test the blade's strength, they smite a metal barrel with it. Incredibly, it doesn't chip. Next, they pump wax into the molds to make historically accurate copies of the hilt parts, like the pommel, which is the counterweight at the end of the hilt, and the guard that separates the blade from the handle. They use the wax copies to cast the parts in metal. Then they grind and polish the cast metal pieces. They smooth away the rough edges on this sword guard and hone its profile. Grinding the pommel is a challenge because it has more curves and angles. One mistake and the pommel could end up lopsided, which means it wouldn't be very effective as a counterweight. With the blade in a padded vise, they slide the guard onto the tang and cushion it with a piece of plastic and a metal pipe. Then they pound it into position with a sledgehammer. Next, they pommel the pommel into place. Then they top it off with a small piece of steel called a peen block. They blast it with a torch. This softens the peen so it spreads as they hammer it down. They apply epoxy to the wood grips and spread more epoxy on the handles of the sword. Then clamp the grips onto either side of it. Next, they brush black dye onto a thin piece of leather and coat the other side with glue. They wrap the glue and dye-drenched leather around the wooden handle. They bind it with cord to compress the leather wrap while it dries. Now they're ready to brand the blade with the marker's insignia. Chemicals etch the mark into the steel, a millimetre deep. And now you have a replica that's true to the medieval original. And it will take you back in time. Now where's that damsel in distress? Party barge, floating bridge, or luxury raft. Some of the many functions of pontoon boats. While a pontoon's basic design hasn't changed much over the years, new marine materials have made these crafts bigger, sleeker, sturdier, and faster. In the old days, 45-gallon steel drums kept pontoons afloat. That rudimentary technology has certainly evolved. Modern boats have custom-built floating chambers made of a special aluminium alloy. Floating chambers start off as sheets of aluminium. This rolling machine forms them into tubes. To curl the metal, the roller in the center applies pressure equivalent to the weight of 26 elephants. A worker slides each cylinder onto a track to stabilize it for welding. A pacing machine regulates the speed of the welding torch so that it joins the tube's edges evenly, producing a solid, watertight seal. This rolling machine, meanwhile, shapes aluminium sheets into tapered cylinders called nose cones. The operator manipulates hydraulic pressure and rollers to mold the aluminium into the right shape. They use a special aluminium alloy to make the chambers shockproof. Next step, turning the nose cone into a leak-proof chamber. First, the welder clamps the nose cone together to position it for welding. Then he begins to fuse the metal seams. The unique shape of this piece requires manual welding. This type of welding, called TIG welding, generates temperatures that can reach 5,000 degrees Celsius. The nose cones will sit at the bow of the boat, in front of the other floating chambers. The waffled component at the end of each chamber is called a baffle. It gives extra protection against leaks. This hydraulic press squeezes the sections together for an extra snug fit. Chambers are welded together to form floats. The number of chambers per float varies depending on the pontoon's length. These risers will hold the pontoon's floor in place. Each chamber floats on its own, so even with several punctures, the boat would stay afloat. A worker injects compressed air into each chamber to check for leaks. He coats the welds with a soapy solution which will bubble up in the case of an air leak. Workers install aluminium cross members that will easily support all the weight that has to be added on top. A worker uses a pneumatic torque wrench to bolt the cross members into the risers with rust-proof nuts. They construct the boat's floor from sheets of pressure-treated plywood. They drive these pop rivets through the wood, anchoring it securely to the cross members. Workers custom cut and glue down a marine carpet. Its fibers are plastic, so even with all that water, they won't rot. Now for some fade-resistant decals to festoon the pontoon. Rollers crimp aluminium side panels to make them stronger. Corrugated panels don't warp or wobble as much as flat ones. A worker fastens the panels onto the railing. This shaping machine curves the railing in all the right places. It bends the soft, malleable metal with progressive pressure. Workers bring the assembled pieces to the platform. A mixture of different screws and bolts secures everything onto the boat's floor, including the furniture. The pontoon's captain will control everything at the helm with this console. The switches for the horn, lights, music and breakers sit at the top of the console for easy access. Extra touches bring some of the comforts of home to this craft. Wires and control cables connect the captain's console to this 50 horsepower motor. It's by no means a high-speed engine, but it gives the pontoon all the power it needs for a leisurely spin on the lake. Hello, sailor. Coming up after the break, grandfather clocks, a manufacturing process that takes time. and fuses. We're enthusiastic about this one. See you after the break. Welcome back to How It's Made. When you wind up a grandfather clock, the cables wrap around a drum inside the mechanism, drawing the weights all the way up. Gravity then pulls the weights down gradually, unwinding the cables that rotates the drum, which turns the gear wheels, which moves the hands off the clock. Tickety-tock. The proper term for this type of timepiece is a long case clock. The nickname grandfather clock came from a popular song in the 1800s. This long-established company makes its clock cases out of quality hardwoods and veneers, such as maple and oak. To construct frames for the four sides and door, workers fit dowels into holes, then solidify the connecting parts with screws and glue. They lay each frame in this curing machine. It uses high-frequency radio waves to generate heat and dry the glue in seconds. Workers connect the four frames with screws and glue. Later, they'll attach the door frame with hinges. The next step is to assemble a base, again with dowels, glue and screws. Once the glue is dry, the assembled frames go into the base. Now for some embellishment. Computer-guided routers carve elegant wood mouldings that'll give this particular model a traditional flavour. Today's grandfather clocks come in styles to suit any decor, from ornate antique to modern urban chic. Workers carefully sand every single piece of wood making up the clock case. The surface must be smooth for it to absorb colour evenly. The mouldings adhere with a combination of glue and nails. These long pieces of wood become curved, fluted mouldings. They adorn the side of the door frame. This model also has a pair of stately columns above and below the flutes. A worker first positions them with glue, then, like the flutes, screws them securely to the frame from behind. The next step is to stain the wood, hand rubbing it to bring out the grey. A coat of lacquer protects the wood and gives it a degree of sheen, from matte to glossy, depending on the model. After installing the glass and door, it's time to install the clock's components, starting with long metal bars called chime rods, 8 to 12 of them depending on the model. Each chime rod produces a certain note when struck. Next comes the movement. This contains the weight-driven components that keep time and trigger the chime hammers to hit the chime rods on the hour, half hour or quarter hour. The brass chime hammers have plastic tips. This muffles the sound of metal striking metal, so you only hear the note each rod produces. These brass pulleys hang from cables connected to the movement. The pulleys will support the clock's 3 weights. After connecting the movement to the clock dial, a worker inserts this model's last decorative detail, a wood panel, to frame the dial. Then she installs the clock's second hand on a shaft in the centre of a miniature dial. On the centre shaft of the main dial, the hour and minute hands. Depending on the model, the aluminium hands are painted either black or gold. A decorative nut secures them. Finally, the all-important weights and pendulum. The weights are brass canisters filled with lead. Each one weighs almost 4 kilograms. The pendulum sways from side to side at an even pace. This ensures the clock keeps time consistently and accurately. It also drives the clocks to chime on the hour or fraction of the hour. All you have to do for Grandfather Time is wind him up about once a week. Fuses have been around since the 19th century, and they're still part of the grid. Fuses are designed to blow whenever there's a strong power surge. This stops the flow of electricity and prevents electrical fires. So by handling power overloads, fuses also take a big load off your mind. Choosing the right fuse depends on your current needs. To make a high-voltage fuse, this machine cuts notches in a long silver strip, which will serve as its element. The notches will help control the way the fuse blows. They melt bits of soft metal onto the strip. The bits will be the points where the fuse blows. They weld one end of the silver element to the top of a ceramic core, and then wind the element around it. This kind of high-voltage fuse will be used in electrical substations. They slide the element core into the fuse casing and bend back metal tabs. Then, using a soldering technique called brazing, they seal everything together. They take a brass washer and wind ignition wire around it. They're assembling the striker pin, the device that indicates a blown fuse and shuts down the power. They press fit the striker pin to the washer, and with the wire protruding, place it in a holding device. They add explosive powder to each striker pin. Then they plug the bottom of the pin with a rubber stopper. Then they press the striker pin into a brass capsule, which will contain the mini explosion that pushes out the pin when the fuse is blown. This test run shows how it all happens. They wrap the pin's ignition wire around an electrical post. They clamp down the pin and position the pendulum that swings to indicate the amount of force with which the pin fires. A jolt of power detonates the explosive. This causes the pin to protrude, signifying a blown fuse. Now they slide a metal eyelet onto the striking pin's ignition wire, and then attach a wire coil to it to complete the ignition system for the striker pin. Using a snare, they pull the whole assembly into the fuse. They tie the end of the coil to the fuse's cap. And they press fit an outer cap over the inner one. They fill the fuse with a specific type of sand. It's a filler that absorbs energy from the element when the fuse blows. Automated rods tap the fuses to compact the sand inside. Next, they lubricate an outer cap for the other end of the fuse. And they press it onto the fuse. This machine spins grooves onto the cap, pinching it lightly to the fuse casing. They run a current through each one of these fuses, checking the voltage throughout to confirm that it's in good working order. They pump sealant around the rims of the caps to make them completely airtight. Finally, they affix the safety information and stamp specifications onto the caps. Now these fuses are ready to go with the electrical flow. And if there's trouble, they'll blow. So, whether you're looking for something fancy for down your local nightclub, or maybe the idea of being captain floats your boat, or it's simply time for one of these, now you know how it's made. Today on How It's Made. Bumpers. We embark on a collision course. Lighting gels and camera filters, helping us see things in a different light. Steam-powered models. They'll transport you to another era. And candy canes. Their story is sweet and syrupy. But first, with all the attention we pay to high-tech automotive components these days, it's easy to overlook the importance of a vehicle's bumper. About 80% of car accidents are front or rear collisions. The bumper is designed to hit the other car's bumper and absorb the force of the impact, minimizing damage in low-speed collisions. Bumpers can be made of plastic, fiberglass, aluminium or steel. This company makes steel bumpers. They start out as blanks, steel sheets just 2 millimeters thick. These ones are en route to becoming truck bumpers. A robot feeds each blank through a series of dies, 7 to 9 of them, depending on the bumper model. Each die stamps the blank to a particular shape using 2,000 tons of force. This progressively forms the blank into the final bumper shape. Both the front and rear bumpers go through the same process, only the dies are different. The bumpers now travel to the next production area, where a worker clamps each one onto a specially designed cart. At this point, the factory paints certain models. These bumpers, however, will get a chrome plating. First, they travel through a series of buffing wheels. The bumper surface must be impeccably smooth because the chrome finish magnifies even the most minuscule flaw. A computer-guided crane stacks the bumpers and maneuvers them through the chrome plating process. It first submerges the bumpers in several cleaning tanks to remove any residue that previous operations might have left on the surface. The chemicals used are a closely guarded secret. The first plating tank applies a coat of nickel to protect the steel from corrosion. The next tank applies the chrome layer. The factory uses the standard electroplating process. In the water and chemical-filled tank, it laces particles of the plating metal with a positive charge and runs a negative charge through the bumpers. This magnetically draws the particles onto the bumpers in an even layer. After a thorough rinse, the bumpers enter the inspection area. Workers scrutinize the chrome mirror finish under high-intensity light. Meanwhile, this machine pressure injects molten plastic into various molds. The machine's built-in cooling system hardens the plastic within seconds. Then out come the plastic components that attach to the bumpers. One of those plastic parts is the step pad that covers the top of the rear bumper. Once the pad's in place, a worker attaches a tow bar and steel mounting brackets that also structurally reinforce the bumper. The front bumper goes down a different assembly line. A worker attaches a plastic trim that hangs down just below the bumper. Its aerodynamic shape helps direct airflow to the engine compartment. 4 steel reinforcing brackets attach the bumper to the truck's frame. Finally, the last components, the number plate holder and fog lamps. Workers tighten all the bolts to a specified torque. This ensures that the bumper and its mounting brackets will adequately absorb the force of a collision. Whenever a new model goes into production, the first few bumpers off the line go through a battery of tests to ensure they can withstand stress, vibration, and a certain degree of what engineers call crash energy. Other types of bumper systems use a combination of springs and energy-absorbing material, such as plastic foam. With either method, the goal is for the bumper to absorb the impact. In a low-impact crash, this should ideally confine the damage to the bumper itself, leaving the headlights and engine unscathed. Smash it! Gels and filters can turn a bad scene into a good one. Technicians use them to colour lights in the theatre, enhancing the scene on stage. They also use them in camera work to even out a mix of colour temperatures from different light sources. In both cases, they help make things picture perfect. These lighting gels can make any scene take on a different hue. They're called gels because they used to be made of gelatin film, but today they make them out of transparent polyester. They mix a batch of solvent, dye, and flame retardant chemicals. This produces a coloured lacquer. They test the lacquer's thickness by pouring it into a brass cup with a hole in the bottom. As the lacquer drains out of the hole, they time how long it takes. If it flows too quickly, it means the lacquer is too thin. If it drains too slowly, it's too thick. A steady flow means the lacquer is made to the perfect consistency, about as thick as engine oil. A sample of every batch undergoes this test, because the lacquer's consistency is critical. If they don't get it right, it won't bond to the clear polyester. With the lacquer prepared, they load the polyester film into the coating machine. A large roller soaks up the lacquer from a tray below and spreads it on the film. A thin bar on the roller evens the spread and scrapes off the excess. The lacquer dries in seconds. Every production run of the same colour has to precisely match the last, so they regularly test the colour of the lacquers on swatches of clear polyester. If gel colours are even slightly mismatched, using them together will make for a patchy-looking job. Different coloured gels create different effects. This orangey red one will warm up daylight, so it's more like indoor lighting. Now, in a test, they hold a gel swatch over a flame. The gel doesn't catch fire, proving that that batch is ready for the hot lights of the stage and screen. At another station, they're working on a different sort of colour changer, a filter that goes on a camera lens. They dip a sheet of special optical plastic in hot water and dye. The hot water opens the pores of the plastic, and this allows the dye to penetrate. When it cools, the colour is trapped inside the plastic. The longer they leave the plastic in the dye bath, the deeper the colour. They dye just half of some sheets to make filters that reduce the exposure of half the camera image. Filters made from a range of colours will help the camera's eye do what the human eye does naturally, adjust to different lighting conditions. They sheath the coloured sheet in thin plastic. This prevents scratching as they cut it to size. These camera filters are almost ready for your close-up. All that's left is for the inkjet printer to brand them. A similar type of printer gives the lighting gels the trademark stamp. And it's time to wrap things up. They slide a cardboard core into a machine that winds the finished gel sheet onto it. And a pneumatic ram pushes the roll of lighting gel into a plastic bag. Now these filters and gels are ready to show things in the best light possible. Coming up on How It's Made, steam-powered models, technical toy-tastic, and candy canes. A very, very sweet story indeed. See you after the break. Welcome back to How It's Made. When they build live steam models, they're reconstructing history. They take us on a nostalgic journey, back to the days when steam ruled the rails and the roads. And for hobbyists, firing one up is a great way to let off a little steam. Add a little water. Light some fuel for the boiler, and it's full steam ahead. This mini replica of a 19th century traction engine is really a blast from the past. It starts with the boiler. A hydraulic press punches a piece of brass repeatedly. This action turns the brass into a cylinder. It's a process called drawing, and it also strengthens the metal. From a flat piece of brass to a cylinder in a few minutes. Next, they trim the ends of the cylinder. They brush solder paste onto a brass cap and slot it into a holding device. They brush the paste onto attachments inside the cylindrical boiler. Then they press fit the boiler and cap together. The capped boilers travel through a furnace, which melts the solder paste, fusing the caps to the cylinder. They polish the brass to give it a sheen. Then they solder copper pipes to the boiler. These pipes will expel the steam as it powers this little locomotive. They trim the flywheel, which is being precast. The flywheel will smooth out the engine's firing impulses so that it runs more evenly. They screw the flywheel tightly to the crankshaft. They check the sliding action of the piston and its cylinder. Then they attach the assembly to the engine frame and the crankshaft. Lubricating the piston assembly enhances its sliding action. They test it with compressed air instead of steam. They check how it functions and look for leaks. Once it passes, they install the front steering mechanism, which will control the steam model's front wheels, while the larger wheels at the back will be powered and will push it forward. Steam machines are usually rear-wheel driven. A wire called the drive band moves the energy from the flywheel to the rear wheel. They hook up the steam model to the compressed air tank once again for a final test run. And it looks like this model is ready for some action. All it needs is a canopy. They punch a ribbed design into a little steel roof. And after a nice paint job, they attach it. Now you have a model that's geared to bring back yesteryear. This model will also take you back in time, but in high style. It's a luxury touring car. They install the piston cylinder assembly a little lower on this roadster and fire it up. Each of these mini steam models is a tribute to the original. They all help to relive a time when vehicle ignition meant lighting a match and really burning some fuel. In the 17th century, a German choir master decided to put a new twist on the sugar stick. He had some bent into shepherd's crooks as a special treat for his choir. And that's believed to be how the candy cane was invented. But it wasn't until more than a century later that they earned their stripes. Today, candy canes come in different stripes and sizes. They start by cooking up a big batch of sugar, water and corn syrup. Next, they prepare a mix of starch and flavouring, like peppermint or strawberry. As they blend them together, the flavouring binds to the starch. They empty the flavouring mix into the middle of the syrupy slab. Then they feed the whole thing into a machine that uses shovels and a plunger to fold the batch repeatedly. This distributes the flavouring evenly. Cold water piped into the shovels and the kneading table cools the candy cane mix so it takes on a stiffer consistency, perfect for the next step. It's over to the automated pullers. These pullers stretch the candy around a metal post. This action aerates the candy, turning it white. There's enough here to make 3,200 candy canes. But there's a lot more work to be done before this job is licked. They roll the candy into a flat log, while heaters warm it, making it pliable enough to shape. Next, they roll strips of red-coloured candy. A worker then stretches and folds the red batch to widen the strip. They arrange 2 of the red strips on either side of the cylindrical mould. It weighs over 45 kilograms, so it takes 2 workers to carry it to the next machine. It's called a batch roller. Cylinders roll the candy thinner in a process that will dramatically reduce the diameter of the log to candy cane dimensions. A torch moves across the candy to keep it pliable. Then the sugary batch travels between wheels that slim it down even more. Now it's a rope of candy, and it exits in a wave-like fashion. This gives it some slack so it doesn't stretch as it moves through another set of wheels. The candy rope moves through 2 angled belts that twist it, and a chain of knives cuts the twisted rope to candy cane size. This production has been perfectly choreographed. One misstep, and the job would hit a snarl. Here, a roll of cellophane unwinds, and a device wraps it around the striped candy stick. Pipes blast hot air to shrink the cellophane on the ends of the canes. Once they're wrapped, these candy sticks finally get their crooks. This machine, called a crookadeck, bends the ends of the candy sticks to turn them into canes. A bracket brush overhead secures the canes gently, because although they're pliable enough to bend, they're still fragile. There's a camera inside this robotic arm, which allows it to spot the candy canes on the conveyor belt and pick them up 2 at a time. It places them in cardboard packages, filling them up by the dozen. It takes about half an hour to make a box of candy canes. And they're sure to come to a very sticky end in a lot less time than that. So, whether you're a driver with a tendency to lose your way a little, or an actor famous for your colourful performances, or perhaps you're a talented toy tinkerer, now you know how it's made. Today on How It's Made. Umbrellas, the reigning champion of weather protection. Outboard motors, vroom to manoeuvre. Silver cutlery, we spoon feed you the whole story. And tape measures, they go the whole 9 yards or meters to make them. But first, it provides shelter from the rain, protection from the sun, and for the stylish at heart, it's a chic fashion accessory. The umbrella originated in ancient China some 1,700 years ago. Since then, it's evolved from the original parasol to the modern-day collapsible canopy that pops up all over the world. Unlike mass-produced models, this quality umbrella is meticulously handcrafted. The shaft is made of birchwood, which the artisan stains to match the umbrella's handle. He trims down the diameter of the shaft so it will fit perfectly into the handle. After buffing the handle to a shine, he glues it onto the shaft. The artisan forms two springs from wire made of nickel silver, a type of metal that can withstand extreme tension. He bends one end of the wire into a triangular shape and hammers it flat to ensure a perfect fit in the shaft. He cuts two slots in the shaft, one at the top and one at the bottom. Then he pierces a hole in each slot where the spring will hook into it. With a bit of stain, he hides the exposed wood. For the umbrella to open and close easily, the springs must fit snugly. So he makes a right-angle bend at each end of the spring. That shape sets the correct tension. With the tap of the hammer, the spring now rests firmly inside the slot. After trimming the spring, he purposely overbends, then corrects it to ensure the perfect shape. A small pin prevents the spring from opening fully, holding it inside the shaft. This brass runner is what you slide up the shaft to open the umbrella. A stop pin limits the runner's travel, preventing the canopy from blowing inside out. He fits a length of tying wire around a slot in the runner, then threads the canopy's 8 ribs onto the tying wire. The ribs are made of a type of steel that's strong yet flexible, so they curve into a dome shape when you open the umbrella, then straighten out again when you close it. He wires the rib's other ends to what's called a notch. Once wired into the notch's opening, the ribs rest just below the handle line. At the spot where the notch will sit on the shaft, he drills a hole for the pinning wire that holds it in place. They cut 8 triangular-shaped panels, called gores, from durable nylon. They attach a label, then assemble the canopy by sewing all 8 gores together. A worker now inserts 8 metal tips onto the horizontal mandrel of this machine. It wraps fabric around each tip, then stitches them to 8 locations inside the canopy. These smaller pieces of fabric, called prevents, stop the canopy from chafing against the frame. This decorative rosette hides the point at which the runner and ribs meet. Next, they drape the canopy over the shaft and hand sew it tightly over the notch. They attach a tip over the end of each rib, then align each rib with a canopy seam. After checking the fabric for imperfections, a worker secures the ribs in position by sewing them to their respective seams. Finally, they roll up the umbrella to check that the fastening button and band, attached earlier, are where they should be. They finish off the umbrella by jamming a decorative ring over the notch. Then they crown the top of the shaft with a ferrule, a brass cap with a protective steel tip. This company embellishes its shafts with a silver-plated band, ideal for engraving the owner's initials. After a quick wash, they iron the canopy for a neat, crisp finish. The final touch is a matching cover, one you can slide off in an instant if you're caught in a sudden shower. Outboard marine motors come in a variety of sizes and horsepower, ranging from single-cylinder configurations to powerful 8-cylinder models. They can run on petrol, diesel, or electricity. And they can be used for anything from a quiet day of fishing to an exhilarating offshore drag race. An outboard motor has an engine on top and a gear case below. This aluminium engine block is the skeleton that houses the cylinders, the heart of the engine's internal combustion system. Under a stream of cutting fluid, machines hone the cylinders to precise dimensions. They carve minuscule X's into the steel that lines the cylinder walls. Oil will settle into these X's, keeping the walls well lubricated for the piston moving within. Workers assemble each piston manually. First, they build a ridged bearing. They insert it into the loop at the end of the connecting rod. Then they fit the rod into a piston head, securing it with a pin. They place one piston in each cylinder. Then they lower in the engine's crankshaft and connect it to the loops at the ends of the connecting rods. Workers lubricate the crankshaft's bearings and cap them. Then they close up this part of the engine with an aluminium cover. To get the cover's positioning just right, they drive the first bolt manually. Then a precision torque wrench does the rest. Now they close up the top of the cylinders. They mount a flywheel on a magneto system on top of the crankshaft. As it spins, it generates electricity for the engine's electronics and pumps. Meanwhile, on another assembly line, the gear case takes shape. This machine locks the case's forward gear to a shaft that'll turn the motor's propeller. The propeller shaft connects to this, the lower drive shaft. The factory buys it ready-made from a supplier, but still has to refine the dimensions so that everything fits together perfectly. This machine analyzes the shaft. It concludes that this one needs to be 0.25 millimeters longer, so workers add the required number of steel discs, called shims. They insert this shimmed lower drive shaft into the gear case, then insert the propeller shaft with the forward gear. Now the gear case is linked to the drive shaft, which connects to the propeller shaft, which turns the propeller. Workers take the middle section of the outboard motor, the part in between the engine and the gear case. First they attach the gear case, which has since been fitted with a shift rod for switching gears, and an upper drive shaft to transfer power from the engine to the propeller. They coat the unit with paint that's specially formulated to be resistant to salt water. When the paint's dry, workers bolt the engine on top. They plug the engine into a master computer. It automatically uploads the operating system into the engine's internal computer. Then, using a scanner, they input information about each cylinder. The motor is now fully operational. Workers insert a propeller onto the propeller shaft, then lower the motor into a test tank. This factory tests each and every motor it produces. They run the engine for 10 minutes, while a computer analyzes the performance data. After drying the engine thoroughly, workers apply the finishing touches, starting with the two-part cover that encases the lower portion. Then they latch another cover over the engine and stick on decals. Both covers are made of heavy-duty plastic, coated in paint that won't fade, despite extreme exposure to sun, wind, and water. Coming up after the break, you'll have to fork out for one of these as we look at silver cutlery and tape measures. It's a lengthy process. See you after the break. Welcome back to How It's Made. Prehistoric people made knives from splinters of hard stone. They used shells, horn and wood chips as spoons. During the Bronze Age, man found a better material, metal. Forks came along much later, originating in ancient Greece. Cutlery. Let's tuck in. Whether cutlery is sterling silver, silver-plated or stainless steel, the production process is the same. It all starts with the given metal in sheet form, between 3 and 4 millimeters thick, depending on the utensil. They feed the sheet through a press manually. A die inside punches out utensil shapes called blanks. Fork blanks go one by one into a piercing tool, which slices away 3 strips of metal. This creates 4 prongs, with a support bar across the top, for now. Spoon blanks, meanwhile, go into a machine called the cross roller. It expands the spoon head sideways, thinning out the metal at the same time. Then it's into a clipping tool, which trims the spoon head to precisely the right size and shape. Both spoon and fork blanks now go into a machine that grinds their rough edges smooth by vibrating them against small plastic cones. Elsewhere in the factory, a specialised tradesman sculpts the steel die that'll stamp the pattern on the cutlery handles. Working from the designer's illustration, he has to interpret the pattern in 3 dimensions. This requires tremendous skill because the depth of the design varies from one point to the next. He measures these minute variations with a tool called a micrometer. In the press, the die does 3 things. It embosses the pattern, bends the handle to the final curve, and marks the back of the utensil with the manufacturer's name and cutlery material. Now back to the head of the utensils. The forks go into a press that bends the prongs to the right curve. Now that support bar can finally come off. Spoons, meanwhile, go into a press that contains what's called a bowling die. It strikes the spoon's flat head into a bowl shape. Every time you strike metal, it hardens a bit. So repeatedly during the shaping process, workers have to heat the blanks to soften them again. Making knives is more complicated than making spoons and forks. The factory constructs the handles from 2 halves. After presses punch them out and stamp the pattern, a clipping machine removes the excess metal around the perimeter. Now workers coat the edge with flux, a chemical cleaner. The surfaces have to be spotless to bond properly. They join 2 halves, then wrap them together with cotton string. Then they pour in powdered metal. It immediately sticks to the flux on the edges. They discard the excess, then run the handles through a mini furnace for 12 minutes. The 900 degrees Celsius heat liquefies the metal powder, soldering the 2 halves together. The string burns off in the process. After polishing, the solder line won't show. Workers pour cement into the centre of a centrifuge machine. Unload the hollow handles all around. As the machine spins, it fills each handle with cement. Now each handle gets a stainless steel blade. The blade stem goes directly into the wet cement. A clamp holds the parts together for now. Next, they submerge the knives in hot water for 12 minutes. This cures the cement, making the handle-blade connection rock solid and giving the handle weight. For worker safety, it's only now near the end that they sharpen the blades. Now for the big finish, a polished one. You can't help but take a shine to these beauties. Many jobs just wouldn't measure up without this trusty tool. The spring-driven retractable tape measure was invented in the middle of the 19th century, but it didn't really become popular until the 1940s. Today, no handyman would be without one, because without it, they wouldn't be, well, very handy. Measuring tapes take the guesswork out of any job, and if you don't use one, you'll soon see the error of your ways. They start with a three-dimensional computer design. A machine then pulls hardened strips of steel 5 at a time across a network of rollers that coat them with paint primer. The next series of rollers paint the strips. After the paint dries, it's time for a rewind to cue them up for printing. Printing cylinders roll measurement markings onto the steel strips. They use black ink for millimeters and red for meters. Next, they heat the measuring tape. This will allow a protective plastic film, applied by this machine, to stick to it. Rollers then give the tape a concave contour so that it can be extended rigidly. The press is slow to a crawl for a second, and a blade cuts the tape to the correct length. At the same time, it punches a hole for the end hook. They rivet the hook onto the tape. Next, another machine rolls up steel to make springs. The spring will enable the measuring tape to retract into the casing. They clip the end of a spring to an automatic winding machine. A worker places the lower half of the tape measure's casing into position. The machine rewinds the steel spring to transfer it to the casing. They lubricate the spring with a little oil and then install the control brakes that will lock the tape in place when measuring. Assembling the rest of the casing is a snap. They screw everything together. They attach the measuring tape to the spring, and this job is done. Time to test that spring action. Some longer measuring tapes are made from glass fibers, partly because they're lighter. They pull multiple strands of glass through a tub of white liquid plastic and they stick together. The fibers then enter a machine that coats them with more plastic, melted down from hard pellets like these. This transforms the glass fibers into a strong yet flexible tape, the type that's commonly used for surveyors' tape measures. A computerized printer transfers measurements to the tape, a meter a second. Lights illuminate the tape so a camera can check for printing defects. A worker double-checks the print job and also examines each tape for accuracy. Some tapes are more accurate than others because standards vary, depending on the industry or country they'll be sold to. She grades each tape and marks it, so it can be tracked back to the operator. A laser then moves over the tapes to check the accuracy level again. If the reading is off by even a few thousandths of a millimeter, then the measuring tape is rejected. Winding a survey's tape is a manual job. They don't install a spring system on them because that would make them too heavy. After winding, they cut the tape and fasten the end hook to it. As you can see, it takes many steps to make a measuring tape. It's a lengthy process, in more ways than one. So, Whether you want to spend your lolly on a designer brolly, or flash your cash on a speedboat dash, or perhaps you need to fork out for your next dinner party. Now you know how it's made. Today on How It's Made, Scalpels, a story at the cutting edge. Oil paints, let us put you in the picture. British police helmets, making them is really old hat. And ice axes, our report on these mountaineering tools is a real cliffhanger. But first, its short blade is razor sharp and designed to slice swiftly and cleanly through skin and what lies underneath. This surgical knife may be a simple instrument, but using it requires years of intensive training and steady hands capable of great precision. They make scalpel handles from rods of stainless steel. The blades are made either of carbon steel or stainless steel. They're sterile and for one-time use only. The blade steel is extremely thin, less than 0.4 millimeters. It arrives at the scalpel factory in coiled strips. The first machine feeds the strips into a press. A die inside punches out unfinished blades, called blanks. Blades vary in size and contour, but they all have the same slot in the center for attaching the handle. When you flex a blank, it bends out of shape, so the next step is to temper the steel. The blanks pass through a furnace for about 30 seconds. The heat alters the molecular structure of the metal, hardening it. From the furnace, they move through a punching tool that pops them from the strip. The separated blanks stack on a peg. A worker now takes each stack, threads a metal ring through the slots to keep them together, then sends off the blanks for surface polishing. That will restore the metal's original sheen, which the heat treatment dulled. After polishing, workers visually inspect every blank, discarding any defective ones. They transfer the blanks from the ring to a metal rod, using a gauge to measure out the right number. From here, they mount the rods onto grinding machines. Each one picks up a blank with a magnet, then places it in a holder. The holders run the blanks against a wheel coated in diamond particles, a powerful abrasive that smoothly wears down the steel. The wheel shapes and sharpens a cutting angle, transforming the blank into a blade. As the blades come off the grinder, they cling together because the magnet that fed them into the machine magnetized them. To cancel this effect, a demagnetizing machine passes an electromagnet behind the stacks of blades. After a thorough cleaning in ultrasonic cleaning tanks, the blades move on to final inspection. Workers wear rubber gloves to protect their fingers and keep the blades clean. They carefully scrutinize the cutting edges, discarding any blade that's less than perfect. Each and every blade passes through two different inspectors. In the packing department, the first machine covers each blade with a brown paper strip that contains an anti-corrosion chemical. The next machine slips each blade into a foil packet, then cuts the connected packets apart. Each packet bears the blade model number and a tracking code. As the blades come off the packaging machine, an inspector does one last quality check. Then he counts the blades and boxes them. Of course, it's critical that surgical blades be sterile, so the boxes go into a cobalt radiation chamber for about 6 hours, obliterating any contaminants on the blades inside. When the boxes exit the chamber, they're hospital ready. In the operating room, it's simply a matter of sliding the blade onto the protruding part of the handle, called the bayonet. Like blades, scalpel handles also come in different shapes and sizes. Surgeons optimize their dexterity by choosing the handle that's the best fit for their hands, and the best suited for the procedure those hands are performing. Making oil paint dates back to ancient times, when people mixed minerals and other elements with wax or oil. In the 1400s, they refined the process, discovering that linseed oil was ideal as a pigment binder, because it allowed blending and glazing in layers. Hundreds of years later, the colours in those paintings are still vibrant. Today, many oil paint pigments still come from natural sources. The rest are synthetically made. Both types are sold in powdered form to factories that manufacture artistic oil paints. Cuttlefish ink yields brown pigment. Lead produces a specific yellow, and mercury ore a particular red. In the past, pigment also came from stones, tree bark, plant gum, ground up glass, and even arsenic. The company's research laboratory spends about 2 years developing a colour recipe. A chemist mixes specific amounts of linseed oil and pigment in a machine called an automatic muller. It rubs the ingredients together, dispersing the pigment particles throughout the oil. For each sample, the formulation is slightly altered in search of the perfect result. The research team compares the resulting colours and selects the best one. Workers pump the amount of linseed oil specified by that formulation into a mixer. Then they add the precise pigment amount. Most colours are made with just one pigment. The formulation stipulates the precise mixing time and speed. Now they ladled the mixture into a mill. 3 dispersion rollers rub the ingredients between them, separating pigment particles and coating them in oil. The recipe specifies how much pressure the rollers apply, how fast they turn, and for how long they work the mixture. Milling can take hours or even days, depending on the pigment texture. The quality control lab takes samples from each batch coming off the mill and subjects them to a series of tests. Technicians scrutinize paint from both sides of the mill to ensure it's processing the mixture evenly. First, a spread test. They place a heavy brass weight on a blob of paint for a prescribed period of time. Then they evaluate the volume of colour and measure the distance it spreads. If it doesn't spread far enough, they mill the batch some more. Next, a dispersion test. The markings on this gauge indicate the size of the paint's particles in microns, millionths of a metre. If the particles are too big, the paint needs more milling. Finally, they time how long it takes the paint to dry to the touch. Each colour has a specified drying time, ranging from 2 days to 2 weeks. The factory produces a labelled chart to display its 120 paint colours. Workers brush each colour onto a primer-coated paper. When the paint dries, they cut each bar into rectangular swatches called chips. Workers assemble the chart using this mounting machine. The bottom has a section for each colour. The top holds a cardboard chart that has information about each colour. After loading stacks of chips and coating the chart with glue, it's just a matter of mating the top and bottom of the machine. A chip for each colour adheres to its designated spot on the chart. Back on the production line, the factory packages one colour at a time in toothpaste-style tubes with a twist cap. Once the labels go on, the tubes make their way to the filling machine. There, the tubes are aligned for closure. A nozzle squirts the paint in, then clamps flatten the end. A roller folds over the edge to strengthen the seal. These oil paints are finally ready for their brush with fame. Coming up on How It's Made. Police helmets. Cop a load of this one. And ice axes. For cool climbers everywhere. See you after the break. Welcome back to How It's Made. British bobbies are used to standing tall because of their distinctive helmets. British police helmets are approximately 30 centimetres high. The rounded shape fits snugly on the head. But even so, they still add quite a bit of height to the policeman. And that can't hurt when you're staring into the face of adversity. Times change, but the bobby's helmet doesn't. It's looked the same for a century and a half. Today, they use a metal mould to replicate it in fortified plastic. The mould descends into an oven. A worker places a sheet of plastic overhead. He lowers the lid and slides a heated cover over it. It takes a couple of minutes for the heat from above and below to soften the plastic. The mould rises, and a vacuum below pulls the plastic to its shape. It hardens almost instantly, and he taps it with a rubber mallet to release the helmet shell from the mould. Using a bandsaw, he slices away the excess along the brim. And the helmet is now ready to be covered. For that, they use water-repellent wool. They cut out halves of the helmet pattern. And then they stitch the two halves together, making a raised seam, which gives the helmet a nicer line. They've coated the inside of the fabric covers with glue. They steam one. Moistening it will make it easier to work with. Then they brush glue all over the helmet shell. The fabric cover is now damp, making it easier to pull over the glued surface of the plastic helmet shell. They stretch it so it fits tightly and doesn't buckle. Then, using a wooden tool, they smooth away any remaining air bubbles. They trim the brim to tidy it up. They sew rubber piping around the brim to reinforce it and give it a neater edge. They dip the prongs of some decorative metalwork in a chalky powder and use it to mark its positioning on the crown of the helmet. They drill holes where the prongs have left markings. Then they install the metal ornament, folding the prongs against the inside of the helmet. Next, they stitch together strips of tape, plastic and foam to make the helmet's harness and chin strap. They fit the harness assembly inside the helmet. Then they secure it with a serious stapler. They wrap metal banding around the helmet and pin it down. The banding gives the helmet a snazzier look and hides the staples used to install the harness. The ornate helmet plate with the police force's insignia on it goes on the front. They tuck a sponge liner inside the helmet to protect the police officer in the event of a blow to the head. They punch ventilation holes in the sides. And now it's time to size it with a special gauge. They tweeze away any fluff and brush the wool to bring up the pile. Then they attach the label that confirms that the product meets all the specifications. This police helmet is now ready to report for duty. Hello, hello, hello. It takes about half an hour to make one of these helmets, and it should keep a bobby on the beat in high style for quite a while. If you aim to conquer mountains, a couple of ice axes will come in handy. Ice axes were invented in the mid-19th century to help mountaineers get a grip on slippery slopes and pull themselves to the summit. They also use ice axes to stop a fall. They're really designed for peak performance. Talk about a steep learning curve. Climbing with ice axes takes a bit of practice, not to mention courage. To make an ice axe, they start with an aluminium rod. A powerful press bends it into a curve, giving it the basic contour of an ice axe. They flatten and shape the rod in 2 fiery dies. Each die has a top and bottom half, which they lubricate between forgings. The hot forging transforms the metal rod. And it starts to look a lot more like the shaft of an ice axe. The long ridges add strength to the metal, while the other indentations mark where the attachments are to go. The forging creates a small lip around the perimeter of the shaft. They call this excess metal flash. It's easily sliced off by this press. This gives it a cleaner edge and also makes it lighter, an advantage when you're hauling it up a mountain. The aluminium rod has gone through quite a few stages, but now it has a whole new profile. This tub of vibrating ceramic cones will smooth the rough edges of the shaft. Here, a computerized drill makes holes in the recesses stamped into the shaft earlier. These holes will be used to attach other parts. The machine changes the drill bit to a circular blade. Then, guided by computer, it cuts a slot for the ice axe pick. The saw moves to the other end and thins out the area where the handle is to be attached. Using another drill bit, it carves out a hole for the adjustable finger rest. Here we see the shaft that's been milled and drilled, compared with one yet to undergo the process. Next, the shaft gets a protective coating. Then it's time to bring all the pieces of the ice axe together. A worker applies epoxy to the inside of the rubber handle and slides it onto the shaft. The handle has an open end. He beads a little more epoxy onto it and then inserts a steel spike. He rivets the spike to the ice axe shaft. Once it's anchored to the shaft, this spike will come in handy on that uphill track. Plunging it into an icy slope will help the climber maintain balance. Next, he slides a part called the adze into the slot in the head of the shaft. Climbers use the adze to chop steps in hard snow and ice. He secures the adze with nuts and bolts, and then installs the pick. This hooked and jagged attachment will help get the climber up a mountain of solid ice. He tightens the bolts with a torque wrench. After all, a solid job here could be a lifesaver. Finally, he screws the adjustable finger rest to the shaft, just above the handle. And now you have a tool that can help you scale new heights. So, whether you're a surgeon looking for a slice of the action, or an artist hoping to brush up on your skills, or a British bobby with a cool head, now you know how it's made. Today on How It's Made. Bacon. We have all the sizzling details from the production line. Snowblowers. Handy little portable blizzards. And luxury cars, fully loaded for the truly loaded. We have a special two-part report on how they make a Rolls-Royce. But first, when it comes to breakfast, bacon is the order of the day. Or at least the side order. Bacon's popularity actually goes back centuries, when people cured and smoked it in their own homes. But today, you simply have to go to the shop and bring home the bacon. Bacon is now processed and even pre-cooked in factories, where things move along crisply. They start with a load of pork bellies. They toss them around in a big tumbler, and the action softens them so it will be easier to remove their skins. They place each pork belly skin side down on a conveyor belt. The conveyor takes the pork bellies to a long automated blade, which slices the skin away from the meat. The skins drop onto another conveyor belt. They're on the way to being processed into pork scratchings. Meanwhile, the meat pieces head in another direction, towards a device that turns them over, so workers down the line can trim off any remaining pieces of skin. Next, they make a brine solution to cure the pork. This involves funneling salt into a tank of water and mixing it thoroughly to dissolve the salt particles. They add liquid smoke and other flavourings to the curing solution. The pork bellies now pass under an injector head. It's equipped with numerous needles that repeatedly inject the curing solution into each pork belly. They press the prongs of a metal hanger, called a comb, into the pork bellies and hang them on a rack. Then it's into the drench cabinet for a shower in liquid smoke. As liquid smoke bombards the meat, it adds flavour and colour to the surface. They transfer the bellies into a large oven. They spend about 5 hours in here, cooking at a low temperature, which allows the flavouring to permeate the meat. Now it's into a blast freezer for a quick chill down, then into another cooler for a couple of days. The cooling firms the meat, which makes it easier to slice. The pork bellies head to a sizing station where knives trim all the sides. They also pass under a metal detector to confirm that pieces of the metal hanger haven't become lodged in the meat. After that, they stack and wrap the pork bellies and store them in a freezer until they're ready to slice them into bacon. This is called the slice line. Here, they load meat slabs into chutes. The chutes sway back and forth over a blade to slice the meat into bacon-sized pieces. The bacon falls neatly onto a conveyor belt. Another conveyor belt rolls over the bacon slices to secure them while they cook in a very long microwave. As the fat cooks off the bacon, it drains into a trough. It will be used to make gravy and pet foods. The cooked bacon now exits the microwave oven and comes under the watchful eye of the inspector. She discards slices that are broken or not up to par. These wheels then roll the brown sliced bacon onto parchment paper. A tiny electronic eye keeps track of the numbers. Finally, they stack the bacon for packaging. Now that's a job well done. Time to put the coffee on and scramble up some eggs. Red sauce or brown, anyone? Snowblowers first came on the market in the 1950s. Today's machines come in a range of sizes, from smaller domestic models to large metre-wide versions that can plough through deep snow. Since its invention, this alternative to shoveling has really snowballed. A snowblower's rotating blades are called augers. The left and right augers spiral in opposite directions in order to move the snow toward the middle. There, a fan called an impeller swallows the snow and blows it out a chute. Each auger starts out as a blank, a partially formed steel disc about 3 millimeters thick. This press finalizes the shape with about 200 tons of pressure. The bigger the snowblower, the bigger the augers. The press forms the left and right augers at the same time. Then a blast of air ejects them onto separate conveyor belts. Next step, workers take a steel tube, called a hub, and mount it upright on an assembly jig. Then they take an auger and center it on the hub. The hub and auger then travel on a conveyor belt to a robotic welder. The robot fuses the two pieces into a single unit. Elsewhere in the factory, workers construct the steel housing that'll encase the augers. This housing consists of 4 parts. A cup to hold the impeller, a back piece with a hole for the cup, and 2 side plates. This bar aligns the pieces in a holder. First, everything turns upside down, enabling a robot to access the back and weld the cup to the back piece. Then it flips right side up again, so the robot can weld on the side plates. Total construction time, 55 seconds. The housings now undergo an electrostatic paint process. Powder paint laced with a positive electrical charge is drawn like a magnet to the housings, which are laced with a negative charge. Workers inspect the coat and do any necessary touch-ups. Then the housings spend 15 minutes in an oven to bake on the paint. In another part of the factory, workers have bolted on a petrol-powered engine to a painted steel frame. Inside this frame, they assemble the transmission parts, the gear system that transfers power from the engine to the snowblower's wheels and augers. After bolting on the impeller, that black component in the back, they attach a large steel axle to the transmission-driven sprocket. Then they slide the now painted auger and hub units onto this axle. Now the housing arrives. Workers bolt the auger assembly into it. The impeller slides into the cup that's centered at the back of the housing. Then they screw the housing to the transmission frame. The last component is the snowblower's handle, which carries the control panel. There's a lever for selecting different speeds and to change the direction of the wheels and augers. There's also a headlight, so you'll be visible to oncoming cars while clearing snow at night or on a snowy day. And of course, there's a lever you move to choose the direction in which you want to blow the snow. Towards your mate, of course. Coming up on How It's Made, it's a 2-part special on luxury cars, as we check out how they roll out a roller. See you after the break. Welcome back to How It's Made. If you have one of these cars, you may also have a chauffeur, and you travel in privileged circles. A luxury vehicle like this one costs more than the average house in many cities. But a house is just a place to live, and you can really live it up if you have a car like this. As long as there have been cars, there have been models that go the extra mile when it comes to perks and performance. For many, the car they drive is a measure of their personal success, and you don't get much more successful than a Rolls-Royce. These cars start with a hand-welded aluminium body shell that's rigid yet lightweight. Workers handcraft the components for the lavish interior. This gadget stitches wooden sheets together with glue. The veneers have been cut from the same piece of wood. They match the grain, so each side is a mirror image of the other. The technique is called book matching, and the look is seamless luxury. There are 40 or more solid wooden parts in the interior of the rolls. These ones are for the dashboard. They hand finish each of the parts. They polish the wood with special paste to enhance the grain. Lacquer is applied to build a shine on the woodwork. They scrutinize the leather and mark any defects. They'll work around those blemishes, so no imperfections will be visible on the interior upholstery. It will take as many as 18 hides to make all the seats, panels and consoles. They carefully stretch leather pieces onto various components and set the fit with a dryer. Ensuring the sewn leather parts conform to all the curves and crevices on the door panels can be tricky. But these workers, some of them former saddle makers, are expert at the job. They mount the upholstered leather parts to the car and secure them tightly with screws. They fit handles and control panels into the tailored slots. Next, they attach switches, wiring and other controls to the instrument carrier. This framework has been crafted from a single piece of magnesium, so there aren't any squeaky joints. The imposing radiator grille has a purpose besides bringing in cool air. It houses the signature hood mascot and its automated platform. They test the platform to confirm that it rises and retracts. Then they mount it just under an opening at the top of the grille, through which the car mascot will be able to rise. They check the spacing around the cover for the opening to make sure there's enough room for things to run smoothly. The mascot is called the Spirit of Ecstasy. With the mascot in proud position, they're ready to assemble the mechanics of the rolls. So stay tuned. This Rolls-Royce is looking good. The body shell has the long lines of luxury. It's been equipped with flawless leather upholstery and elegant wooden panelling. Plush and posh, this car is now ready for some serious engine power. It's bumper-to-bumper opulence at this factory as these cars queue up to receive their engines. They install soundproofing material on the floor of the car to muffle engine noise. Then they run the wiring loom along the length of the vehicle. This is the nervous system of the car. It transmits huge amounts of information to help run the engine, transmission, even the car's entertainment system. Next, they hoist the engine and transmission system onto a large metal platform. This V12 engine has 400 plus horsepower. With the engine system on the platform, they complete the assembly and make some adjustments. It's time for the engine and car body to become one. They call this the marriage. It's a dramatic sight as the platform rolls the engine down an aisle to be joined in mechanical matrimony. The platform lifts the engine into the cavity of the car. They secure it with bolts. They lower the platform and it retreats to receive an engine for the next car. They double-check the installation and mark parts with yellow to confirm they've been fitted. The engine is now installed. It's time for this car to move on to the next steps. They mount the instrument control panel to the dashboard and cushion it on top with upholstered leather. Next, they fit the veneer panelling around the dashboard controls. They install the head lining, made of cashmere of course. They check the hydraulic coffee cup holders in the rear of the car, but it's not quite time for coffee yet. They install 2 batteries, one for the engine, the other for the cabin controls. They fasten a rocker cover to the engine to stifle any noise. They hook up the air intake system. There'll be no fingerprints on this windscreen. After they wipe it clean, they use a pulley system with suction cups to lower it onto the car. They tape it to allow the adhesive to set and measure it to ensure a perfect fit. Next, they install the wheel arch liners. These hefty guards will protect the car body from mud, gravel and debris. Finally, they mount the wheels. It takes several weeks to assemble a Rolls-Royce, compared to the day or 2 it takes to manufacture an ordinary car. That's why one of these will set you back a princely sum. This car is ready to roll with the high rollers. So, whether you're not after an egg butty, but something a little rasher, or you want to clear your path and beat your mates in a snowball fight at the same time, or you simply want to roll up in one of these, now you know how it's made. Today on How It's Made. Automatic transmissions. Gearing up for production. Silver miniatures. At this factory, scaling down means business is good. Hot air balloon baskets. The sky's the limit. And darts. We get right to the point of this story. But first... The transmission in your car transfers power from the engine to the wheels using the appropriate gear for your driving speed. With an automatic transmission, the driver doesn't have to change gears manually. The car's computer determines when it's time to change and sends an electronic signal to activate or deactivate the appropriate gear. The transmission is a system of gears and levers that transfers power to a car's drive wheels while allowing the engine to operate in its most efficient range or power band. It's assembled inside an aluminium housing called the transmission case. At the heart of the transmission are 3 sets of planetary gears, the term for smaller gears rotating around a larger central gear. The first gear set is called the final drive. It harmonizes the engine speed and driving speed and is attached to the differential, a component that lets the wheels move at different speeds so the car can turn. They install the steel parts connected to the gear lever, which puts the car into drive, reverse or park. First, the manual detent lever. Then the forward clutch support. This piece protruding from it is called the park pawl. The actuator rod connects the detent lever to the park pawl, which locks a gear that immobilizes the car when you change into park. Now for the transmission's 5 clutches. Clutches either let gear sets rotate or lock them. This clutch is called the forward clutch. It enables the car to advance when you change into drive by moving the 2 remaining planetary gear sets, called the input gear set and the reaction gear set. 2 clutches, installed as one unit, go in next. The coast clutch controls both the input and reaction gear sets, enabling the car to coast in low gear and progressively brake in higher gears when you take your foot off the accelerator. The other one is called the direct clutch, which locks the 2 gear sets so there's no reduction in speed. Next, the reverse clutch. When in reverse, it moves the reaction gear set, enabling the car to back up. A clutch is made up of layers of metal and friction material, such as resin-impregnated paper. The transmission's last clutch is called the second clutch. It uses both the input and reaction gear sets to switch the transmission into second, third and fourth gears. With all the gear sets and clutches now in place, workers can connect the transmission to the rest of the car's electronics. These cables are known as the harness. Next comes a drive chain and 2 sprockets. This hookup is the critical link between the transmission's gear sets and its torque converter. The torque converter is the component that transfers power from the engine to the transmission. The sprockets, along with the final drive, convert the engine speed to the appropriate transmission gear. The car's computer directs this hydraulic control system to change gears as needed. The computer triggers an electronic switch, called a solenoid, to open a specific control valve. This applies hydraulic pressure to engage the clutch around the relevant planetary gears. The system releases hydraulic pressure to disengage the clutch and lock the gears. Now the final connection for the shifting mechanism, linking this manual valve to the detent lever. The gear lever moves the detent lever, which makes the valve direct hydraulic pressure accordingly. This steel bar, called the output shaft, directs transmission power from the final drive at one end of the transmission to the driver's side front wheel at the other end. Next, they install springs and servos, part of the hydraulic control system that help engage and disengage the clutches smoothly. This tube assembly goes in next. The control valves route hydraulic fluid through these tubes to the different clutches. Now the torque converter. It spins a shaft that turns those sprockets and drive chain we saw earlier. A steel bar called the stub shaft is the final link, sending transmission power from the final drive and differential to the front wheel on the passenger side. Did you get all that? Because it came automatically to me. Collecting miniatures and displaying them in dolls' houses isn't just child's play. It becomes a serious hobby for grown-ups, who even buy fine silver in miniature. They spare no expense, because after all, it's the little details that make the difference. In the world of miniatures, there's no need to downsize one's expectations. Here you can find all the little luxuries, like fine silver that isn't just a cheap reproduction. This silverware is a tiny version of the real thing. To make it, they use silversmithing tools and techniques that have been handed down over generations. This is a workbench used in the 18th century. Today, they use one that's nearly identical. They measure a full-sized mug and divide the measurements by 12, giving them specifications that are 1/12 the scale, but true to the original. Next, they squeeze a strip of silver between rollers, which thins it to about 1/2 millimeter. Then they punch small round shapes from the silver. A blast from a torch softens them, which makes them easier to work with. They plunge them into acid, which eats away any impurities and leaves a frosty finish. Next, they spin one of these silver discs on a lathe, and using a series of tools, they shape it into a thimble-sized mug. Any mistake is a big one when you're working with such small dimensions. It could ruin the whole job, so they work with great care. The machining also removes the frosty finish left by the acid wash, for a truly sterling result. They buff up the mug to add luster to the finish. Next, they make a mini silver base for the mini mug. They taper it so it will be a perfect fit. They place small fragments of silver solder between the two pieces. Then they heat the parts to 770 degrees Celsius to fuse them together. Next, they cut up leftover silver and put the scraps in a crucible. They add a pinch of borax, a mineral that will prevent unwanted oxides from forming as they melt the silver leftovers to a molten mass. Melting the scrap will enable them to reuse it. They pour the molten silver into a plaster mold of little handles. Then they plunge it into cold water. The temperature change causes the plaster to explode, exposing the mini silver handles. They solder one onto the little silver mug. And now it won't slip through your fingers quite so easily. Next, the miniatures are cleaned and polished by friction in a bucket of steel shot and soapy water. They strain out the soapy water, revealing the gleaming miniatures. Each silver miniature has to meet the same standards of purity as full-size silver. Here in Britain, the regulations have been around for 700 years. The maker's mark, called the hallmark, is the stamp of authenticity. Hallmarking a miniature can be a bit awkward, and sometimes the article is just too tiny to mark. But when it comes to replicating silverware, it seems no job is too small. And there are plenty of shining examples in the world of miniatures. Coming up on How It's Made, hot air balloon baskets. A jet may be quicker, but it's not made of wicker. And darts. We step up to the hockey and aim for the bullseye. See you after the break. Welcome back to How It's Made. Did you know that some hot air balloon baskets are more than 6 meters long and carry more than 30 people? The bigger the basket, the more passenger compartments it has, preventing people from toppling over each other during bumpy landings. Some say you'd have to be a basket case to get in the first place. First, you build the frame. Workers cut pieces of tubing made of stainless steel. They manually round the corner pieces, then assemble the frame by welding all the parts together. They cut a sheet of plywood for the floor, then drill holes in it for stainless steel support cables. The cables reinforce the floor against the weight of the passengers. After marking off the area that the basket walls will occupy, workers run the cables under the overturned floor, leaving extra on both ends to come up the sides of the basket. Then they notch a groove, the width of the cables, in runners, lengths of ash wood that protect the base of the basket and give it rigidity. After bolting the runners down, workers use a branding iron to burn the company logo into the floor. Then they spray on a coat of lacquer to prevent moisture from rotting the wood. Larger baskets need diagonal reinforcement cables for extra support. The basket walls are made of cane, the stiff stems of a tropical Asian plant. The cane soaks overnight in a water tank. By morning, it's supple, and the weavers can begin their craft. They start by installing uprights, attaching each one to the frame at the top and bottom with a thin piece of cane. Then they feed the support cables from the floor up through the frame. The uprights are 45 centimeters apart along the sides and 10 centimeters apart around the corners. The weavers fill the gaps with thinner uprights every 5 centimeters. Then they tie them to the frame and floor with rope. With all the uprights installed, it's time to build the basket walls from the bottom up by interlacing horizontal canes. A pair of weavers can finish a small basket in a day, whereas large baskets can require a 4-person team and take up to 3 weeks to weave. They use 2 techniques: randing, going in and out with 1 cane, and whaling, weaving 3 canes at once. Whaling makes a more solid basket, but one that's significantly heavier because it requires triple the amount of cane. Some models have stainless steel steps woven into the basket. These give passengers a foothold when climbing in and out. The weaving ends just below the top of the frame. To finish, they split the remainder of each upright down the center with a utility knife. Then flatten and wrap what's left around the frame. The weavers integrate rope handles at the top of the basket, giving passengers something to hold onto during the ride. They also put handles at the bottom for carrying the basket. Now they pad the frame with foam, cutting holes to let the support cables through. The foam is for both comfort and safety. It cushions the hard metal during a bumpy ride. After taping the foam pieces together to prevent shifting, they slip on a leather cover. and thread a polyester lace through the eyelets to close it up. Finally, with a few bangs of the hammer, they expose the short tubing to which the load frame will connect. The load frame carries the burners high above the basket. A heating coil surrounds each burner. To make it, they wrap a stainless steel tube around a form, then rivet on a reinforcement band. The basket carries lightweight fuel tanks containing cold liquid propane. The propane flows upward into the coil. When the pilot fires up a burner, the flame heats the coil, transforming the propane flowing inside from liquid to gas. The gas feeds the flame, which heats the air inside the balloon. Hot air is lighter than cool air, so the balloon responds by rising to the occasion. Up, up, and away. The game of darts dates back to the Middle Ages, when English soldiers looking for some fun began pitching arrows at the bottom of an empty barrel. When winter came, the soldiers moved their games indoors. But they couldn't throw big arrows around inside, so they used shortened versions, and the game was on. With these little missiles, you can give this game your best shot. They start by making the flight shafts. That's the piece that the dart's wings are attached to. They load 3mm aluminium rods into a machine that has several cutting tools. The tools work from many angles on one aluminium rod at a time. They shape the rod into dozens of shafts. The tools cut threads and hollow out one end of each shaft to allow it to be screwed onto the dart barrel later. A cross saw cuts slots in the other end for attaching the wings. Oil flushes away the shavings and keeps the machinery cool, so it stays sharp enough to cut through metal. The completed shafts fall into a bin to await further assembly. Next, they load brass rods into a similar machine. Its tooling carves the brass rods into barrels. That's the main part of the dart that you grip. They thread and taper one end to allow the shaft to be screwed onto it. The tapering also makes the dart aerodynamic. Next, tools with angled grooves cut ridges on the outside of the barrel to make the dart easier to grip. The process is called knurling. Another tool then cuts the brass barrel to the correct length. They also make dart barrels from tungsten, which is quite dense, so the barrels can be cut slimmer. Slimmer darts can give you an advantage in tight scoring situations. It's why the pros often prefer tungsten darts and have them custom made, even choosing their own knurl grip. These are the knurling wheels. It's another way to etch the grip pattern into the dart barrels. Knurling wheels come in an assortment of patterns, all designed to help you keep a grip on your game. And now, production takes a very sharp turn. They force a pointed steel tip into the hollowed end of the dart barrel using a hydraulic press. With the point now snugly in the barrel, this dart is ready for its wings. They're made from polyester film, which first winds through printing rollers. Some print jobs involve just one basic colour, while others layer many colours to build up a design. In the world of darts, the wings are known as flights. A machine cuts out the flight shapes, and they accumulate in big piles. Flights are made in various shapes. This is just one. They fold the cutouts together to make a flight. They check each one for symmetry. Now it's time to screw the shaft to the barrel of the dart. They slide the polyester flight into cross slots on the end of the shaft. And this set of darts is now ready for its target market. It takes less than a minute to make a dart, but it can take a lifetime to find the bullseye, especially if you play like me. So, whether you're gearing up for a change of pace, or perhaps convinced that size really doesn't matter, or maybe you're on your way up in the world, now you know how it's made.